Alrighty, folks, so moving into the final lesson for Unit 2 here, we're going to talk about rational functions today. We did polynomials, we did radicals in the previous lesson. Now it's time to just talk about rational functions. So then we'll be done Unit 2. You can do your Unit 2 test, your Topic 2 quiz. And yeah, after that we'll be on to Unit 3. Hard to believe, it's going fast, eh? Okay, so here are the big ideas. As always, you can use them as a little bit of a checklist to check in with yourself at the end of the lesson after you've done your practice. Are you able to apply those skills and do those things and answer those questions? If not, that's fine. Maybe it means you need more practice, or maybe it means you got to reach out to me. Either way, I'm always happy to help. But let's get going here and starting to talk about rational functions. What are they? Well, you might recognize that term rational from Math 20. We talked about rational expressions and rational equations in Math 20. You can probably guess. Now we're going to look at rational functions. So we did rational expressions, rational equations. Now we're going to say what happens when we have a function that's equal to one of those rational expressions. Okay, so a rational function, all it is now still, is a function with an equation that contains polynomials in its numerator and its denominator. So at the end of the day, a rational function, it's in the key word there, ratio. It's a ratio. It's a fraction. It's just a special type of fraction that has a polynomial in the numerator and a polynomial in the denominator, like we can see there or there. If you need a reminder on what that means, what's a polynomial? It's just something that contains multiple terms with variables being added together or subtracted, right? The terms are separated by addition. For example, this is a 3-term polynomial in this numerator. It's got an x cubed term, a 4x squared term, and a 5 term. The constant term, the x squared, and the x cubed, right? So the terms are separated by addition and subtraction. And then each individual term is made up of a coefficient, 4 for this one, a variable, x, and an exponent, 2, or x squared. So this means that a rational function can just be written as f of x is equal to p of x over d of x, where p of x and d of x are just placeholder names for polynomials. So like we've been looking at, some examples of some rational functions, right? X squared plus 5 over 3x minus 1. That's a rational function. Y is equal to this. Like any other function, we're going to put in x's. We can see what y is. We could draw the graph of it if we do that for enough x's and y's, right? That's all a rational function is. Y is equal to this stuff. We input x's, y gets output. Here's a very simple rational function, 1 over x. 1 is technically a polynomial. It's a monomial that just has a constant term. X is also technically a polynomial. It's a monomial, one term with x, okay? This one's going to become important because remember how we used y equals root x as our base function for radical functions? We thought about performing transformations to it to describe other radical functions, This is going to be a similar situation for us with rational functions. It won't be quite as universal as root x was for radical functions, but it'll still be pretty helpful for a lot of different rational functions. So, an important note here, a rational function, or expression in this case, in general, a rational expression, is defined for every value of the variable except for those that make the denominator equal to 0. Nothing too shocking there, because if the denominator is 0, that means we are dividing by 0, right? You can't divide by 0. Can't divide by 0. It makes no sense. How do you split something into 0 groups? That's not possible. Can't divide by 0. Okay, so for example here, we could not have x equaling 0. We'd be dividing by 0, right? Here we could not have x being 1/3, because 3 times 1/3 would be 1, and then 1 minus 1 would be 0, right? So we call those the things that x is not allowed to be. They're not permitted. Very creative name. They are non-permissible values. Values that make the denominator equal to 0 cannot be input to a rational function because, again, dividing by 0 is undefined. So we call these values non-permissible values. We often call them NPVs for short, okay? We sometimes call them restrictions or limitations. They all really mean the same thing. Restrictions on x, things you are not allowed to make x equal, okay? All right. Now, with those non-permissible values, or at least I mean, we'll talk about asymptotes in a couple contexts, but one of the things that asymptotes can be related to is a non-permissible value. What's an asymptote? I know it's probably been a while since you heard that, all the way back to reciprocal functions back in Math 20, probably would have been the most recent time you've heard that term. But an asymptote, remember, it's just a line that a graph will approach but never touch or cross. Now I got to be careful there. There are some asymptotes that can be crossed, but this part always holds true. The graph will approach it as x goes to infinity or negative infinity, or sometimes as y goes to infinity or negative infinity. The graph does get closer and closer to it, but it doesn't reach it. Okay, let's first talk about, there are two types of asymptotes that we're going to look at here. There's vertical asymptotes and horizontal asymptotes. There are other asymptotes called slant asymptotes that we don't cover in Math 30, but they're pretty cool. Okay, let's start with the vertical asymptote. So if we think about it, a vertical asymptote, it's a vertical line, or I should say, it's not part of the graph. That's a key thing here. Okay, this is not part of the graph. It is a line that the graph is approaching. So sometimes students say, oh look, the graph has a straight line here. Well, not really. The graph is actually approaching that line, but it's never able to reach it. Okay, so if we think about that, what's it approaching? It's approaching a value of x, right? In this case, x is 0. As x gets closer and closer to 0, okay, our graph gets closer and closer to x being 0, but we can see it's never actually getting there. Okay, it gets closer but doesn't reach it. That's a vertical asymptote. The graph approaches an x value but doesn't reach it. So these can occur at x values which can never be put into the function. In other words, x's that are non-permissible values, right? Note that MPVs don't always result in asymptotes. They can also cause points of discontinuity. This is just a little look ahead. We will see cases where there's NPVs, but they don't actually lead to an asymptote. Okay, we'll look at that later. They can cause what's called a point of discontinuity. But the point holds here. It's some value of x that the graph approaches but never reaches. So as the graph gets closer and closer to these non-permissible x values, it's going to shoot up to y equals infinity or down to y equals negative infinity. Now, let's just take a second to think about this. Why would there be these vertical lines that the graph would approach? Why would it happen at the non-permissible value? Well, let's take a look. This is the graph of y equals 1 over x, okay? Y equals 1 over x. And it's showing us that if we graph it, we can see there's a vertical asymptote at x equals 0. Well, we can see why x can't be 0, right? If x were 0, we'd be dividing by 0. That's not allowed. So why does this graph, why is it undefined when x is 0? Well, then we'd be dividing by 0. So why this graph can never actually go there, because y can never actually equal 1 over 0. That's undefined, right? So if it did, right, because if it did, we'd have a division by 0, which is undefined. We know the graph can't go there because all the graph is showing us is every combination of y and x that can satisfy this equation. Well, x being 0 can never satisfy this equation, so the graph can never pass through x being 0. Okay, similar here, vertical asymptote at x equals 3. Same idea. If x were 3, we'd be dividing by 0. So x can get very, very close to 0, and that's the other thing, right? Can x be 0.0000001 here? Absolutely. Nothing wrong with that. We can divide 1 by 0.0000001. But what will happen, and that leads into what they're talking about here, is if I divide by something very close to 0, I get a really big answer, right? Like 1 over 0.1 is 10. 1 over 0.01 is 100. 1 over 0.001 is 1,000, right? So it starts shooting up pretty quickly. Y gets really big there. Same thing if I do it from this side. If x becomes like negative 0.1, y is negative 10. If x is negative 0.0001, y is negative 10,000. I lost track of how many zeros I said there, right? But it gets very big in the negative direction there as x gets closer and closer to 0. Very similar logic here. X can be 2.9999. Then we have a very, like a negative 0.0001. We're dividing by a very small negative number, so we end up with, you know, y becoming very large. So why does the graph go off to y equals infinity or y equals negative infinity as it gets closer to these x values? Well, I'm going to write this out here. As x gets closer and closer to the asymptote, which for these here is the NPV, okay, what's happening to the denominator? So as x gets closer and closer to 0 here, or as x gets closer and closer to 3 here, what's that mean for our denominator? It's getting really, really, really small, right? Like when this is 3.00001, this is just 0.0001, right? Denominators, the denominator gets very close to 0. Okay. That means we're dividing by a very smaller and smaller number. So we're then dividing by a very small number. And if you divide by a very small number, what do you get? You get a really big answer, right? When you divide by something very small, the result is very large. And so since y is equal to, you know, stuff divided by some denominator, okay, if that denominator is getting very, very close to 0, we're dividing by a tiny, tiny number, which means our result for y is going to be really, really big. Whether it's a really, really big positive or negative depends on the other stuff happening in the equation, but regardless, it will get really, really big, right? Like when, again, when x is 2.9999999, the function's still defined, but this is now like negative 0.000001. So if we take negative 1 and divide it by negative 0.000001, we get y equaling a really big positive number, right? That's why it's shooting up to infinity there. Same thing here. When x is 0.000001, 1 over that is going to be a really big y. So look what's happening. As x gets closer and closer to 0, y is shooting up to become larger and larger and larger, okay? So that's the vertical asymptote. We will find them at our non-permissible values. Just, again, worth noting in the back of your brain, not all non-permissible values are always going to lead to vertical asymptotes. They can also lead to something called a point of discontinuity. I know that seems a little mysterious for now. When we see points of discontinuity later, I promise it actually makes a ton of sense why they don't have an asymptote, but the function is still undefined there. So save that for later. Okay. What about a horizontal asymptote? This is where the graph approaches a y value, right? Just to spoil it a bit. Horizontal asymptote is a sideways line that the graph approaches. Again, it's not part of the graph. It's where the graph is approaching, okay? But y now is approaching that, okay? It's getting closer and closer to that y value. So this one has a horizontal asymptote at y equals 0. You can see the graph is getting closer and closer and closer, closer and closer and closer to 0. Closer and closer to 2 for this one, closer and closer to 2, but not reaching it, okay? So these occur at y values which the graph approaches, but does not reach as x approaches infinity or negative infinity. So in other words, as x goes off to infinity, like the end behaviors of the graph, right, y is just getting closer and closer to some value, but not reaching it, okay? So consider this. Why would we have horizontal asymptotes? Why would there be some y value that we approach but can't ever reach? Okay, well, let's take a look. It's asking us this here. Y equals 1 over x. What x, if any, could you input to make y equals 0? So let's sit here and think about this for a sec. If x were 1 billion, would y be 0? We're dividing by a really, really big number. But would we get 0? No, right? We'd get a tiny number. We'd get like 0.0000001, but we wouldn't get 0. If we made x 100 billion trillion cajillion, right? Still, would y be 0? No, it would be tiny, 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 but it would never actually be 0, right? We can just picture as x gets larger and larger and larger, y does get closer and closer and closer to 0, but it's never actually going to get there. And same goes for when x goes to negative infinity. As x approaches negative infinity, a similar thing happens. Y approaches 0, it just does it from the negative side, right? If x is negative 1 billion, y is a tiny, tiny, tiny negative number, but it's not 0, right? And that's what you kind of see happening here. As x goes to negative infinity, y is approaching 0. It's not going to get there, but it's approaching it from the negative side, from below, right? Here, as x goes off to positive infinity, what's happening to y on our graph? It's approaching 0. Now it's doing it from above, from the positive side. But again, as we see, the equation shows us it's never actually going to reach 0. Okay, so for what value of x could we input to make y equal 0 here? None, nothing. There's no value of x that could actually make y equal 0 here. No matter how large x is, y will never actually be 0. Right? Again, if x equals 1 billion, then y is 1 over 1 billion for this one. Which is, what's 1 over 1 billion? It's 0. Got to count my zeros here. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's a tiny number, but it's not 0, right? It's tiny, but it's not 0, which is tiny, but not 0. Okay, so as x goes to, so for this one, so for y equals 1 over x, as x goes to positive or negative infinity, this is just saying, this math notation is saying as x approaches positive or negative infinity, as it gets larger and larger and larger in either direction, y gets closer and closer to 0, but it doesn't reach it. Sound familiar, right? That's just the definition of a horizontal asymptote. A value of y that the graph will approach but never actually reach, right? And so for this specific example, we would have a horizontal asymptote at y equals 0. And that's exactly what we see when we graph y equals 1 over x, right? For all those reasons we just talked about. You can see here as x goes to positive infinity, y does get smaller and smaller, getting closer and closer to 0, but never reaching it, right? Similar example here, and the equation can help us out, right? Sometimes it's helpful to just imagine what happens as x becomes huge. Well, this gets closer and closer to 0. So overall, what does y get closer and closer to when x gets huge? Well, if this is getting closer to 0, then y is getting closer to 0 plus 2, or 2, right? Sure enough, look at our horizontal asymptote. It's at y equals 2, right? When x is 1 billion, this is basically 0, so y is basically 0 plus 2. Now, it's not, but it's very, very close to it. It's getting closer and closer. Same thing on the other side, but from the negative thing, okay? So that one has a horizontal asymptote at y equals 2. You could sit here all day and try to come up with a way to make y equal 2, and you won't be able to. No matter how big you make x, this won't quite be exactly 0. You can make it tiny, but you can't make it 0. And therefore, you can make y very close to 2, but you can't actually make it 2. And the bigger you make x, the closer you make y to being 2, but you'll never actually get to there. Okay? okay? So knowing the equation of the asymptotes first is actually an awesome tool for sketching the graph of a rational function, because think about it, right? If you know places where the graph approaches, that gives you a pretty good idea of how to like end your graph, right? It's really helpful for graphing, right? If I know that my graph's going to approach this line and it's going to approach this line, I kind of know how to at least, finish those parts of the graph. I can send them towards those lines. They're going to get closer and closer to those asymptotes without reaching them. So if you draw in the asymptotes, and then you think about the behavior of y as x approaches the asymptote or goes to positive or negative infinity, you'll have a pretty good idea of how the graph behaves generally already. With a few points, and remember, you've got the equation, or at least if you're sketching the graph, you probably have the equation, okay? So with a few points, plug in those x's. You can get those points by plugging in x's, I should say, right? To figure out what y would be. You can then start filling in the details pretty well. So let's try this out. Let's try sketching the graph of f of x equals 1 over x plus 3. So we'll complete the table below, think about the important features, and then we'll use it to help us sketch the graph of this thing here. So the vertical asymptote, where will it be? Well, remember, that's a value of x that the graph can approach but never actually reach, right? So looking here, it's going to be at our non-permissible value, right? So what value of x can this approach but never actually reach? It's going to be -3, right? X plus 3, if we have 1 over x plus 3, x cannot equal -3, otherwise we're dividing by 0, right? X plus 3 cannot equal 0, so x cannot equal -3. Subtract 3 from both sides if you like. So we'll have a vertical asymptote at x equals -3. So I'm going to add that. I like to do the asymptotes right away because those give us a pretty good idea. Now I know my graph will approach that, but it won't reach it. Okay, because if it did reach it, I'd be dividing by 0. That's not going to show up on our graph because you can't divide by 0. All right, what about the horizontal asymptote? Well, for that, remember, ask ourselves what would happen as x went to infinity or -infinity, because that'll tell us where the horizontal asymptote will be, right? So taking a look here, I've got 1 over x plus 3. As x becomes huge, when in doubt, put in a big number, right? Put in 1 billion. This is 1 over 1,000,003,000 when x is 1 billion. So what's that getting closer and closer to, right? That's almost 0. It's not quite 0, but it's getting closer and closer to 0, right? When x is 1,000, this is a small number. When x is 1,000,000, it's an even smaller number. When x is 1 billion, this is an even smaller number, but it's never actually 0. It's getting closer and closer without reaching it. Same thing happens as x goes to -infinity, except y would now be negative. If y equals 1 over -1 billion, right? It's a tiny, tiny negative number. So it will be approaching 0, but it'll be doing it from down here. So it looks like we have a horizontal asymptote at y equals 0, right? As x approaches plus or minus infinity, y approaches 0. Okay. And believe it or not, we actually have got a really good idea of what this graph does now, because we know it approaches both of those lines, right? That gives us a good idea of the behavior of the graph. If we just kind of fill in with a few points here, we'll be on our way to just finishing this thing off, right? Already I kind of know it's positive when x is greater than -3, right? And it's approaching this, and it's approaching this. So that's a pretty good shape of it already. It's negative when x is less than -3, because then my denominator's negative, right? If x is -4, my denominator's -1. So overall, y is negative. So it's doing, something like that. It's approaching those two asymptotes. To get a little more clear and, some definition on our graph here, all we can really do, or all we really need to do anyway, is fill in some points, right? We've got an equation. Don't forget, what does a function do? You can put x's into it, and it will tell you the corresponding y, and that will be a point that's on your graph. So let's do it. I suggested some points here just for the sake of ones that I happen to know will work out nicely. So if we put in -4 for x, then f of x, right? I mean, it's just 1 over -4 plus 3, which is 1 over -1, which is -1. So for this graph, when x is -4, y is -1. So x is -4, y is -1. It's kind of where we predicted it would end up. Okay, what about when x is -5? Well, -5 plus 3 is -2. So that's 1 over -2, which is -1/2 or -0.5. So when x is -5, y is -0.5. I'm going to add that point to my graph. Just like we'd expect, right? As x is getting bigger in the negative direction, y is getting smaller because we're dividing by a bigger and bigger negative number, right? Y is getting closer and closer to 0. Yes, it's going up, but its absolute value is getting smaller. It's getting closer and closer to 0. Okay, when x is -6, I'm going to have 1 over -3, right? -6 plus 3 is -3. So 1 over -3, -1/3, or if you like, -0.33, which just means when x is -6, it's about 1/3 of the way to -1. Something like that. Okay. Honestly, after that, I feel pretty good about drawing my graph there, right? Like, I know it's going to do this. It's going to approach this. Whoa, that wasn't very good. It's going to approach this. It's going to approach that line. Okay, that's pretty solid already. Now, sorry, I don't like the way I drew that. Should always be getting closer, but never actually reaching. Something like that. Okay. Now, if you're wondering, well, how did I know that it was going to shoot down to -infinity? Honestly, I just thought about it. What happens when x is really close to -3 coming this way on the negative side, right? So like when x is -3.1. Let's just look at that. When x is -3.1, what do we get? We get 1 over -0.1, which is -10. What about when x is -3.01? So coming from the left here, getting closer and closer to x being -3. We know x can't be -3 or we'd be dividing by 0. Whoops. There's supposed to be a +3 there. Well, that would give me 1 over -0.1, right? 1 over -0.01, which is -100. See what's happening? As x gets closer and closer to being -3, y is just getting bigger and bigger and bigger in the negative direction. If I make x -3.001, I get -1000. So that's why it shoots down so quickly. I only changed by 0.01 there, right? I added one extra 0. And look what happened. It shot all the way down from -100 to -1000, okay? And so we're getting this dramatic drop, right? We can think about it. When x is really close to -3, our vertical asymptote, y becomes really, really big and really negative when we approach this way, okay? Let's get some other points here. 1 over -2 plus 3. So when x is -2, y is 1 over 1, which is +1. So when x is -2, y is +1. There's a point on my graph. Like we predicted, if x is greater than -3, my denominator is positive, and so y is positive as a result, because it's just 1 over a positive denominator, right? What about when x is -1? Then I'd have -1 plus 3, that's 2. So when x is -1, y is 1 over 2, or 0.5. And when x is 0, I have 1 over 0 plus 3, or 1 over 3, which is 0.33, right? So when x is 0, y is 0.33, 1/3 of the way to 1. When it's -1, it's 0.5. And again, if we're wondering, okay, I know it's going to approach this asymptote. I know it's going to approach this asymptote. I don't feel super comfortable knowing how it's going to approach, though. Think about it, right? What happens as x gets really close to being -3, but it's doing it this way, right? When x is -2.999. Well, this is going to be positive 0.0001, right? So it's going to be shooting up. 1 over 0.001 is 1,000. So y is getting really big in the positive direction as x gets closer and closer to that value of -3. Okay, similarly, as x goes off to positive a billion, well, 1 over a billion is basically 0. It's not, don't get me wrong, but it's getting very close to being 0, right? The bigger x gets in the positive direction, the closer y gets to 0. And the closer x gets to being -3, the larger y gets, but now in the positive direction because we're approaching this asymptote from the right, right? When x is, again, just to visualize, if x is -2.999, well, then y is going to be 1 over positive 0.001, which is 1,000, right? When x is -2.9999999, it's gotten even closer. We're going to have 1 over 0.0000001. So y will be an even bigger positive number. And that's why it's shooting up to positive infinity there. Okay, now it's asking us what is the domain and range of the function from the previous example. We can use our graph to tell us the domain and range. We can also use the equation itself, right? Remember, domain is the x's that we can input. What x's are a problem here? There's really only one, right? It's -3. X just can't be -3. X could be anything else, right? You could sit here all day and try to think of x's that would give us a problem, but the only problem we would run into here is if we divided by 0. And the only way to do that would be to make x be -3. So if x were positive, negative, 0, anything else, it's fine, right? The only value for x that cannot be input is x equals -3. And the graph confirms this. Look, it extends to the left forever, hitting every x all the way down to -infinity. It extends to the right forever, hitting every x all the way up to positive infinity, but it never goes through x equals -3, right? So it's all real numbers. The graph passes through all real numbers for x except for -3. So what's our domain? Well, there's just one thing to say. It's the set of all x's such that x does not equal -3. But other than that, x can be any real number. Very similar story for our range. The only y we cannot get out of the function is, and again, the equation backs us up here, right? No matter what we make x, we'll never be able to make y equals 0, right? But we can make it be pretty much anything else we want it to, right? The graph confirms this. I can see that y extends up forever to positive infinity. It extends down forever to -infinity. However, it never actually touches 0, right? It approaches 0 from above, it approaches 0 from below, but it never actually gets there. So for our range, again, really just one thing to specify, and that's that it's the set of all y's such that y does not equal 0. Y is an element of the real numbers. All right, cool. All right, so now that we've done a little introduction to oh boy, not radical functions, rational. I gotta fix that. Whoopsies. Now that we've done a little introduction to rational functions, okay, you probably, or you might have guessed, we're going to now talk about transforming them, much like what we did with radical functions, right? We introduced ourselves, talked about them, and then we talked about how we can transform them and use those transformations to think about any radical function, just thinking about how it's like y equals root x, but having been changed around in certain ways. Now we're going to do that with our base function, instead of being y equals root x, being y equals 1 over x. A small note here, This is actually not going to work for every rational function. We'll see those later. Some of them just aren't in the correct form to be able to look at them this way. They're not like 1 over x. They're like some other function. But this can still give us a good chunk of functions to talk about in terms of thinking about how it's like y equals 1 over x, but having been changed in certain ways. Now, again, it's like Unit 1, right? We're doing the same stuff. It's the same skills, the same ABHK, okay? In fact, we even did some transformations on rational functions in Unit 1 because it was applying those same skills. We're just going to focus in now on doing it specifically to rational functions. So recall, again, our function notation, AF of bx minus h plus k, or our mapping notation. That one's a little more specific to how you actually, what are you actually going to do to every point x, y on the original graph to get an image point on the image graph, okay? But our A just causes a vertical stretch by a factor of absolute value A, vertical reflection across the x-axis if A is negative, because again, we're multiplying everything by A for a vertical stretch. So if A is negative, that's going to change the sign of every y. Positive y's become negative, negative y's become positive. Therefore, they're flipping across the x-axis. Okay. B causes a horizontal stretch by a factor of 1 over b. Again, going a bit quick here because we just talked about this in the radical lesson, but because x is not isolated in our equation. So when we see that bx that it's been replaced with for a horizontal stretch, we realize that if we actually wanted to determine the effect on x, we would have to isolate x and see what happened to it, and that would involve dividing that b on both sides, not multiplying. Okay, and a horizontal reflection across the y-axis if b is negative. Again, multiply every x value by 1 over b. If b is negative, then you're changing the sign of those x values, so you're moving them from the left side of the x-axis or y-axis to the right, or the right to the left. K causes a vertical translation k units upwards, slides it up, or downwards if k is negative. Again, we're just adding k to the y values, so if we add something to y, we're moving the graph up. If we subtract something from y, we're moving it down. H causes a horizontal translation, h units to the right if h is positive, or to the left if h is negative. Again, that's just we're adding something or subtracting something from every x value, so that's obviously going to move the x values left or right, right? Subtract from x, you move it to the left. Add to x, you move it to the right. And it has that inverse operation effect because, once again, x is not isolated. So when we see stuff like x minus 3, h is actually positive there. If we were to isolate x, we would end up adding that 3 to both sides. And we would see that, okay, x used to be equal to stuff. Now x is equal to stuff plus 3. So it's been moved to the right by 3. Okay, now we can apply all of these transformations to the graph of f of x equals 1 over x as well. That's going to be our base function. That's what we're going to think about transforming in order to think about other rational functions. They work the exact same way. They can have the exact same effects on the domain and range. And in this way, we can think of the graph of many, notice I said many, not all, but many rational functions as being like y equals 1 over x, but having been transformed in certain ways. So here is what we get. Y equals a over x minus h plus k. That's what happens when we apply the general transformations for functions to this equation. Okay, I'm going to point something out first, then I'll talk a little bit more about where this comes from if you're feeling a little uncomfortable with it, because you're probably noticing, where's b? Where's b? Well, b, and therefore horizontal stretches and reflections, honestly, we just don't really worry about them in rational functions. They don't really appear in rational functions because including them, including b, would just give us this, a over b x minus h plus k. But since we end up with, notice here, we just end up with a over b. So we can kind of absorb what we wanted to do with b into a anyway, right? Like, for example, if I wanted to vertically stretch it by a factor of 3, let's say I wanted to make a 3, oops, I wanted to make a 3, and I wanted to horizontally stretch it by a factor of 1/2. So I wanted to make b 2, right? Well, notice something here. I could just as easily rewrite this. It's 3 over 2, right? A over b is just 3 over 2. And so I could just write that as 3 over 2 times x minus h. So I could think of it as a vertical stretch by a factor of 3 and a horizontal stretch by a factor of 1/2, but I can actually get the exact same result with a vertical stretch by a factor of 3 over 2. Okay, this is a lot like, remember when we saw the radical functions? You could vertically stretch it, and that would make it taller and narrower, just like pizza dough, right? Stretch it upwards, and that makes it narrower horizontally, okay? So you could vertically stretch to achieve a horizontal stretch anyway, right? You could horizontally stretch it to achieve a vertical stretch anyway, right? Stretch the pizza dough sideways, and it gets skinnier vertically, okay? It gets shorter, so to speak. And so with radical functions, it was still worth thinking about B and A because sometimes B was easier than A, right? It was easier to think about a horizontal stretch versus a vertical stretch. For rational functions, though, that's really just not the case. We can kind of let A do all of the work, and so we can actually just leave B out, right? If I want to vertically stretch by a factor of 3 and horizontally stretch by a factor of 1/2, I can actually achieve the exact same result. We can see that mathematically, because I can just say, well, let's just call it a vertical stretch by a factor of 3 over 2, or 1.5. Okay, does that make sense? So since we end up with A over B anyway, we can achieve any desired horizontal stretch by choosing the correct A, the vertical stretch, right? I even bring up the dough analogy here in the notes. Sort of like how you can stretch dough vertically to achieve the effect of making it narrower horizontally, right? So we keep things simple, and we just let A do the work. Now, returning to this a little bit, where does that come from? Again, like I said, it just comes from taking this, y equals AF of bx minus h, but since we're leaving b out for these, I'm just going to say x minus h plus k, right? Remember, what is this saying? It's telling us how to transform any function f of x in these ways, right? There's no specific f of x involved here. So what if we took a specific f of x, like the one we're interested in today, f of x equals 1 over x, and we applied these kind of instructions to that? What are the instructions here? It says if you want to transform f of x in these ways, you need to, instead of f of x, have f of x minus h. In other words, replace x in the original function with x minus h, right? That's f of x minus h. The same way f of 2 would mean replace x with 2. Put in 2 for x. We're going to put in x minus h for x. And then what does it say to do with f of x minus h? Because that's now what we've found, right? I've put in x minus h as my x. 1 over x minus h. Well, then it says to multiply it by a and add k to get the transformed equation. So I'm going to take that, I'm going to multiply it by a. We can simplify this in a second. And then I'm going to add k. And then a times 1, right? You can think of this as a over 1. So a times 1 is just a over x minus h plus k. And that's where this comes from, right? This is not on your formula sheet, but it doesn't really need to be because this is, right? And you can take it, after having done unit 1, you can take this and say, what would that give me for 1 over x, right? If my function, if f of x was 1 over x, what would we do to it? We'd replace x with x minus h, then we'd multiply that by a, and we'd add k, okay? So this can let us write the equation for a rational function from its graph, like we did with radicals in the previous lesson, or we can graph it from its equation, right? Because if we can pick out those a's, b's, h's, and k's, or those a's, h's, and k's, I guess in this case, then we can fill this in and write the equation. Or vice versa. If we've got the equation, we can start from y equals 1 over x and think about how to change it based on what a, h, and k are. Just don't forget RST, right? Reflections and stretches have to happen before translations because reflections and stretches involve multiplying x and y by something. Translations involve adding or subtracting something to x and y. So multiplication comes before addition and subtraction in the order of operations. Order of operations tells us that. All right, so since we're going to be using 1 over x as our kind of base graph that we're going to think about transforming to think about a lot of other rational functions, let's start out by getting to know 1 over x pretty well, right? If that's going to be our home base, we got to know it pretty well. So what's our domain? What's our domain? Well, we kind of just looked at this one, right? X is everything. X goes up to positive infinity, x goes down to negative infinity, except x is never 0, because then we'd be dividing by 0. So the domain is just such that, oh, I don't have much room here. Forgive me, I'm going to leave out the whole fancy set notation. I'm just going to say x cannot equal 0. X is an element of the reals. What about the range? Well, again, y goes up to positive infinity, goes down to negative infinity, but it's never 0. So y cannot equal 0. Y is an element of the reals. Vertical asymptote, we have that vertical asymptote that's closely related to our domain, right? The vertical asymptote is at x equals 0. It's right here. Drawing it in, ooh, that's not showing up very well, but there it is. You can kind of see it. X equals 0, vertical asymptote. Okay, VA. Right? That's closely related to the domain, which is a result of the non-permissible value at x equals 0. We'd be dividing by 0 if we let x be 0. Horizontal asymptote, again, horizontal asymptote is a value of y that the graph approaches but doesn't reach as x goes off to positive infinity or negative infinity. So we see that here. As x is going to positive infinity, y is getting closer and closer to 0, not reaching it. As x goes to negative infinity, y is getting closer and closer to 0, not reaching it. Which checks out with what the equation tells us, right? Make x a billion, y is tiny but not 0. Make x negative a billion, y is tiny but still not 0. And it's doing it from the negative side then. So our horizontal asymptote is at y equals 0. Okay, the domain for which the function is positive, this is helpful to think about in the context of reflections, okay? Reflections. The reason being is that if I were to say reflect this in the y-axis, I would have something like, something like this, roughly speaking, okay? And you can see then that it's switched. It used to be when x was greater than the asymptote, y was positive, and when x was less than the asymptote, y was negative. Now that's flipped around. When x is when x is less than the asymptote, y is positive, and when x is greater than the asymptote, y is negative. So that's why it's sometimes a good thing to think about where would we expect it to be positive or negative. So the domain the domain for which the function is positive when x is greater than or equal to 0. Generally speaking, we could say when x is greater than or equal to the vertical asymptote. Okay, that's just something to keep in our back pockets when on the lookout for reflections and whether a might be negative and all that kind of stuff. Okay, so that makes sense from the equation as well, because when x is positive, we're dividing by a positive number. In general, when x is greater than the vertical asymptote, we're dividing by a positive number, right? When x is less than the vertical asymptote, or for this graph, when x is less than 0, we're dividing by a negative number, so our y will come out as negative, right? Divide by a positive x, our y comes out as positive. Okay? All right. Alrighty, so let's try out an example here where we're looking at some transformations to our base function, our 1 over x, when we're thinking about, this form of rational function and how we transform it. So the graph of f of x equals 1 over x is transformed into the graph of g of x by applying the following transformations. A vertical stretch by a factor of 2 about the x-axis. So keeping in mind, we're trying to write the equation here, right? It's a good idea to keep track of our parameters, a, b, h, k. Well, no b here, but you get my meaning, hopefully. So a vertical stretch by a factor of 2, that means our a value is 2, right? Every y value is going to get multiplied by 2. A horizontal translation, 3 units to the right. Okay, so what does that tell me about? A, h, or k? That's h. And what is h? Is it positive 3 or negative 3? It's positive 3 if we're translating it 3 units to the right. And lastly, a vertical translation, 5 units down. So that tells us about our k and our k must be 5 units down, so we're subtracting 5 from each y value. K is negative 5 then. Okay, so now we want to figure out what is the equation of the transformed function g of x. Well, again, this is why this is so powerful, right? If we can think of, not all, we'll see ones where we can't quite do this later, but many, many rational functions can just be thought of as being like 1 over x, but having been messed around with in certain ways. The certain ways in this question are these here, right? And that alone can let us write the equation for g of x just from thinking about how we could change the equation of 1 over x to get this, okay? So this is kind of the, the general form for transforming a rational function. Again, it just comes from taking our good old y equals af of b x minus h plus k, and applying that when f of x is specifically 1 over x. This is what we get. So we really do now just need to plug in our a, h, and k. So the equation for g of x is just going to be, well, a is 2 over x minus h, but h is 3, plus k, but k is negative 5, so minus 5. And there we go. There's the equation for g of x. Next up, it asks us, what are the non-permissible values, the NPVs for g of x? Well, a couple ways we could think about this. We know that 1 over x is going to have a vertical asymptote at x equals 0, right? Because that would have us dividing by 0. We saw that up here on when we first introduced ourselves to y equals 1 over x, right? A vertical asymptote at x equals 0. So what's going to happen if we take this thing and we shift it 3 to the right? Well, that vertical asymptote is going to end up at 3, right? The horizontal stretch and vertical stretch won't change that because it's at x equals 0. Sorry, the vertical stretch. Okay, the other thing we can do, probably the more effective thing to do here, to be honest, is to take a look at our equation. We just wrote the equation for g of x. So we can pick out the non-permissible values pretty quick. We're not allowed to divide by 0. What value of x would have us dividing by 0? Well, if x were 3, because then we'd have 3 minus 3, which is 0, and we'd be dividing by 0. So the non-permissible values are that x cannot equal 3. We'd be dividing by 0 if x equaled 3. Where is the vertical asymptote? Well, that's very closely related to what we just said, right? 1 over x has a vertical asymptote at x equals 0, because that would have us dividing by 0. 2 over x minus 3 minus 5 is going to have a vertical asymptote at 3. X can approach 3, but it can't ever be 3, right? 3 is a non-permissible value. So it'll be at the NPV, which is x equals 3. So that will be the equation of our vertical asymptote, x equals 3. Then it says, what is the horizontal asymptote for g of x? Now remember, to find a horizontal asymptote, it's always the same thing, right? What value does y approach as x goes off to the right to positive infinity, or as x approaches negative infinity to the left, right? In other words, like as x gets really, really, really big, what is y getting closer and closer and closer to? Well, if we take a look here, right, just imagine it. As x goes off to positive infinity or negative infinity, what's happening to this stuff here? Just what I'm outlining. What's that getting closer and closer to? Like if x is 1 billion, I've got 2 over 1 billion roughly. That's a tiny number, right? The bigger x gets, the smaller 2 over x minus 3 gets. The closer and closer it gets to 0, right? So let's just think about that. As x goes to plus or minus infinity, the 2 over x minus 3 will approach 0. Now, y doesn't just equal that though. So is y going to approach 0? Well, no, y is going to be approaching 0 minus 5, right? So 2 over x minus 3 minus 5, if this part here is approaching 0, that means it's approaching 0 minus 5, which is negative 5, right? So y is going to be approaching -5 as x goes off to infinity or negative infinity. Because again, as x goes off to infinity or negative infinity, this stuff here approaches 0, meaning that overall, y is approaching 0 minus 5, or -5. Okay, so g of x approaches -5 as x goes to positive or negative infinity. Therefore, where's our horizontal asymptote? It's at y equals -5. This actually, again, makes a ton of sense in terms of translations. Where did y equals 1 over x have a horizontal asymptote? It was at y equals 0, right? Because again, as x goes to infinity, y just approaches 0 for this thing. Okay, what did we do to this? In this graph, we translated it 5 units down. So if we take a horizontal asymptote at 0 and translate it 5 units down, where is it? It's now at -5. Makes sense. Okay, note your answers for C and D and compare to the asymptotes for f of x equals 1 over x. How is this result related to the transformations that were performed? Well, we kind of just talked about that, didn't we? Right? The vertical asymptote was at x equals 0 for y equals 1 over x, but it's at x equals 3 for y equals 2 over x minus 3 minus 5, right? Makes sense. We shifted it 3 units right. Makes sense. We shifted 3 units right. So starting from 0, we're going to end up at x equaling 3. Okay, so this kind of gets at something here. For these in this form, think about it. It's always starting from x equals 0 if we think about on y equals 1 over x, and then we can translate it h units right or left. So our vertical asymptote is always just going to be at h, right? Because it starts from 0. So starting from 0, if we go h to the right, it's now at x equals h. If we go h to the left, it's now at x equals -h, right? Well, still x equals h, it's just that h would be negative. Makes sense, we shifted it 3 units right, so h, the parameter h, tells us the vertical asymptote. We're going to use that fact when we're thinking about them in this way. Okay, very similar thinking for the horizontal asymptote, and we already kind of talked about it, was at y equals 0 for y equals 1 over x, but it's at y equals -5 for y equals 2 over x minus 3 minus 5. Again, makes sense because we shifted it 5 units down. So if it was at 0 originally and we moved it 5 units down, where's it going to end up? -5, right? 0, move it 5 down, it's at -5. So K is going to tell us the horizontal asymptote, because again, it's always starting, if we think about 1 over x as our starting point, our base graph, it's starting from a horizontal asymptote of y equals 0. And so wherever we translate it vertically, the only thing that's going to change that is k, right? Vertically stretching is not going to change that asymptote. Only vertically translating, shifting it up or down will change it. So k directly tells us the horizontal asymptote. And that's what this gets into here, right? Would a different stretch have resulted in different asymptotes for g of x? So if a had been 3 or 4 or 6 or 1 even instead of 2, well, no, right? The stretch always multiplies each y value. And again, our asymptotes are not part of the graph, but what our graphs approach is where the asymptote is. And so if we're multiplying our graphs by some a, that's not going to change that they're approaching 0, right? They're still approaching 0 at those smaller numbers. Only translating can do it. So no, the stretch multiplies. okay, multiplies the y or x values. In this case, since we're just thinking about a, I'll just say the y values. Multiplies the y values by a, okay? Well, since our asymptotes are both at 0, because the graph approaches 0, both vertically and horizontally. Since our asymptotes are at 0, that's where the graph approaches. Multiplying those approaching values by something isn't going to change what they're approaching because 0 times a is still 0, right? And 0 times a still equals 0. The asymptotes are unaffected by stretches. Kind of like, remember the end points when we did radical functions, right? Since it was at 0, 0 to start with for y equals root x, we knew that stretches couldn't change that because 0 times a is 0, 1 over b times 0 is still 0. Similar idea here. Our asymptotes are at x equals 0 and y equals 0 for these 1 over x type rational functions. So multiplying them by some a value isn't going to change them. Only translations will change them. Only translations. Sliding will do that. All right, let's now put it in reversed. We've been talking about, thinking about the graph when we're given the equation. Let's see if we can go from the equation from the graph. Alrighty, so much like we always kind of do with these, right? When we want to go from the graph to the equation, it's really nice to have a base graph like y equals 1 over x because we can compare to what we know that should look like. And we can say, how has this graph been changed compared to that, right? How does this look like 1 over x, but if we had messed with it? Because by doing that, we can work out what a, h, and k must be. What's the vertical stretch that's been applied? Has it been horizontally or vertically translated? And if so, by how much? And if we can figure that out, that's all we need to write the equation of the function in the y equals a over x minus h plus k form, right? All we need to know to do that is a, h, and k. So if we can figure that out by looking at the graph and comparing it to what 1 over x would, normally look like, we can write the equation. So how are we going to do that? Well, we kind of talked about it. We kind of built those ideas up in that previous example, right? First, let's just check for any translations. I mean, again, it doesn't have to be first, but it's kind of a good starting point because it's actually really quick. If you just look for the h and k right off the bat, remember where we saw h and k and how they related to features of the graph? We saw that h tells us directly the vertical asymptote. Again, because y equals 1 over x has a vertical asymptote at x equals 0. And if it's not at x equals 0, that can only be changed by translating it right or left, right? With an h. We know that it should have a horizontal asymptote at y equals 0. That can only be changed by a vertical translation, sliding it up or down. So that directly gives us k. Wherever the horizontal asymptote is now, that's how far we must have slid it vertically. So those can only be changed by translations. So that's what I'm talking about in this section here. Translating the graph horizontally will change the location of the vertical asymptote, and it's starting from x equals 0. So wherever it ends up, that's just how far we slid it. The location of the vertical asymptote tells you the horizontal translation, and therefore a. So right off the bat, just by looking where the vertical asymptote is, we've got 1 down, 2 to go, okay? The other one's just as simple. Translating the graph vertically is going to change the location of the horizontal asymptote, and it's also starting from y equals 0. So wherever it ended up tells us exactly what the vertical translation was, and therefore k. Look at that. Just by finding those asymptotes, 2 down, 1 to go. We know h, we know k. If we can figure out a, we can write the equation, as long as it's one that's in this form. Okay, we will see, like I keep saying, there's ones today where this stuff doesn't really work for because they are not like the graph of 1 over x to begin with, but it works really well for ones that are like the graph of 1 over x. All right. Also, the asymptotes is great. The translations work really well, but when in doubt, you don't have to just be a graph only person, right? You can rely on if the equation kind of makes sense, or what your equation is suggesting makes sense. You can confirm by considering what the asymptotes suggest about the equation in the first place, right? For example, a vertical asymptote at x equals 3, what does that tell us? It tells us that x can approach 3, but can never be 3, right? That suggests our equation might contain something like 1 over x minus 3, right? Because again, if it's shooting up to infinity or down to negative infinity, the closer x gets to being 3, that's telling us, oh yeah, we're getting closer and closer to dividing by 0. We're getting 1 over really tiny numbers when x is really close to 3, giving us really big y outputs, right? And what's more, it looks like x can never actually get to 3. It approaches it, but it can't get there. That's because if we had x equaling 3, we'd be dividing by 0, right? So a vertical asymptote at x equals 3 kind of does suggest that we should have something like 1 over x minus 3 in our equation. So that makes sense too, hopefully anyway. A horizontal asymptote at y equals 2 tells us that y approaches 2 as x approaches positive or negative infinity, but never actually reaches 2. Right? And what does that suggest? Well, it kind of suggests that our equation, as x goes to positive infinity or negative infinity, there's some 2 that's just still there, right? We might have 1 over x. As x goes to infinity, this gets closer and closer to 0, meaning that overall, we're getting closer and closer to 0 plus 2, or 2. And that's why y would be approaching 2, right? And notice that kind of tells us, oh yeah, k could be 2, right? Or here, h could be 3. So it kind of checks out, right? Not only looking at where it ended up and how thinking of it as a horizontal or vertical translation, but also just thinking about what the equation tells us about what those values would mean, okay? Now that we've got our h and k, like I said, 2 down, we got h, we got k. All that's missing to write the equation is a. Honestly, to solve for a, let's just do, probably the simplest way is to solve for it using any other point on the graph we can see. Right? It's great if we can use like a y-intercept or something. That just makes the math work out nicely, but it doesn't necessarily need to be the y-intercept. It's just any point you can see that's nice to read and you don't have to estimate, right? After step 1, we're going to have h and k, meaning all we need to write the equation in this form is a. That would be all that was missing after that. So since any point on the graph of a function satisfies its equation, right, again, all the graph of this is going to show us is every point where the y and x make the equation true, right? Well, we can figure out, if we can see a y and an x to put in, we can figure out what a must be to make that point be on that graph with the h and k that we already know. So we can pick any point x, y from the graph and substitute them into our equation so far in order to find a. We've done that before, right? We saw it with polynomial functions. We even can do it a little bit with radical functions as well. That's often a good strategy. If you're only missing one parameter, in this case a, right? Well, then just pick a point from the graph and solve for that one unknown parameter, as long as it's a good point where you don't have to estimate. Okay, let's try this out. Let's put it to work here in these examples. So it wants us to write the equation of each function in the form y equals a over x minus h plus k. We can do that for these because looking at them, you can tell they do kind of look like 1 over x. They've just kind of been messed around with, right? For example, the vertical asymptote is not at x equals 0, that kind of thing. We will see, again, I know I keep mentioning it, but just want to remind you, not every rational function can always be written in this form or thought of as just transformations to 1 over x, but for these ones, we can tell we're safe to do that because they kind of do have that shape of a rational function like 1 over x, but having been messed with. Okay, so let's pick it out. We got 3 things to find in order to write it in this form: h, k, and a. H and k probably should be our first here. Doesn't have to be, but it's just the quickest and the easiest here. So if we take a look, h, we'll notice my vertical asymptote is at, where is it? It's at -3. Vertical asymptote at x equals -3. Where would it normally be? Where would it be at y equals 1 over x? It'd be at 0, right? So we've translated this 3 units to the left, right? Stretches can't change where our asymptotes are because our asymptotes are at x equals 0 and y equals 0 for y equals 1 over x. So VA at x equals -3, suggesting a horizontal translation 3 units left. And therefore, h equals -3. Boom, 1 down, 2 to go. Look at our horizontal asymptote. It's at y equals 0. Horizontal asymptote at y equals 0. So how does that compare to where it would be for y equals 1 over x? Yeah, it's the same. So have we vertically translated this? No, right? A vertical translation of 0, you could say. It hasn't been vertically translated. So our k is 0. Okay, 2 down, 1 to go. So now we know that our k is 0, our h is 3. Let's just write out what we know, right? So far, we know that y equals some a over x minus h, but in this case, we know that our h is -3, so x minus -3 is x plus 3, plus 0 is our k, so we can just leave that out, right? Plus 0 is not going to change anything. And hey, doesn't this also, we can check our work, right? We can check our work as we go by thinking, ooh, does it make sense that if this is what our equation kind of looks like, that we'd have a vertical asymptote at x equals -3? Well, you tell me, look at that. Would we be able to approach x being -3 but not reach it? Right? Would y shoot up to infinity and negative infinity as x got closer and closer to -3? It would, right? Because if x is -3, we're dividing by 0. We can't do that. As x gets really, really close to -3, y is going to get really, really big because the denominator is getting really, really small. It's getting really close to being 0. We're dividing something by a tiny, tiny number, giving us really, really big y values. That's why it's shooting up to y equals infinity. And most importantly, that's why x is not ever going to equal 3. -3, because then we'd be dividing by 0. So now, I mean, we can call that step 1 if we want. We got our h and our k. All we're missing is a. So step 2, find a. And to do that, it's pretty straightforward. Think about what we've got so far. We've got most of an equation, and this equation is supposed to describe this graph, right? And that means that any point x, y on this graph is supposed to make this equation true, right? That's what this graph shows us, every point x, y that satisfies this equation. Well, we don't know what a is, but we can see some x's and y's that are apparently going to make this graph true. So if we put in those x, y, those points, then we can figure out what a must need to be in order to make that x and y actually satisfy the equation. So pick a point, any point, doesn't really matter. What we should do, though, is pick a clear one where we don't have to estimate. So, like, for example, I might not pick that one where I'm like, oh, is that y value 0.25, or maybe it's 0.3, or maybe it's 0.23, right? Who knows? But these nice clear ones, how about this one? Here, how about that point? So that's at -2, 1. Right? Could have also used this one. That one's pretty good. It's at -4, -1. I'm going to choose to use -2, 1. It's just the one that jumped out to me first. So I'll use -2, 1. So we're going to get that when y is 1. Okay, we've got some a value over when x is -2 plus 3. And see what I mean? Right? We know that -2, 1 is on the graph. We know that h is 3, so now we can figure out, h is -3, sorry. Now we can figure out what a must be if that point's on the graph. So we just need to solve this. So that means 1 equals, I'm going to drop the color coding here, a over -2 plus 3 is just 1. Oh, so a over 1 is just a. So a equals 1. And that was the only piece of the puzzle we were missing there, right? We knew that y was equal to a over x plus 3. Now we know that a is just 1. So our equation is just y equals 1 over x plus 3. In other words, this really is just the graph of y equals 1 over x. All that's actually happened to it is it's been translated 3 units left. Okay, we picked out h from the vertical asymptote, k from the horizontal asymptote, and then plugged in a point to solve for the a value. Not so bad, right? Kind of fun. Let's look at B. Let's get B. So right away, I'm going to give you a second. Maybe try pausing the video. Can you pick out h and k? Well, let's see. I see a vertical asymptote right here. Vertical asymptote at x equals positive 1. Where would it normally be? Normally, as in for our base graph, y equals 1 over x. It would be at x equals 0, right? So it's been translated 1 to the right. And therefore, our h is positive 1. Okie doke. What about k? What about k? Well, k comes from our horizontal asymptote, because again, for y equals 1 over x, it would be at y equals 0, but it's not. It's down here at negative 6. So it's been translated 6 units down. Whoops. Whoops. Not vertical. Horizontal. Horizontal asymptote at x. Oh boy, keep mixing these up. At y equals negative 6. So it's been translated 6 down from where it would normally be. Therefore, our k is negative 6. So look at that. We're 2/3 of the way there, folks. We know now that our y equals some a. We don't know what our a is yet, but we're making progress over x minus h. H is 1, so x minus 1 plus k. But k is negative 6, so that means minus 6. And now we've just got to pick any point we can see on here. Now, one thing to point out, it kind of looks like a reflection has happened here, right? Because look, compare these two where there was no reflection to this one, right? Or even just think about the graph of 1 over x, which looks something like that. It definitely looks like we've had a reflection, right? This is now, do it in a different color. Now it's up here, and now this one's down here, right? Notice how that's a reflection? So we might be predicting that our a will be negative, okay? But we can make that prediction, and then we can back it up by actually solving. So let's now, step 2, let's actually find our a value. How are we going to do it? Pick a point, any point. Just try to pick one that's nice and easy to see, and you don't have to estimate. For example, I see one here that looks pretty good. How about this guy? Bonus, because it's a y-intercept, which just makes the math a little easier because now x is 0. So it looks like it's at 0, negative 2. So using what we've built so far, every y on this graph will be equal to whatever a is over the corresponding x minus 1 minus 6. So for this y, we've got negative 2 equals a, whatever a is, over x minus 1. Whoops, not x. We're picking an x and actually putting it in. 0 minus 1, right? That's the x. When x is 0, y is negative 2. So when x is 0, y is negative 2. When x is 0, y is negative 2, minus 6. And hey, the only thing we don't know in that equation is a, so let's solve for it. So that means negative 2 equals a over negative 1 minus 6. So negative 2, a over negative 1 is just negative a minus 6. I'm going to go ahead and add a to both sides just to get positive a. Not the only way to proceed, obviously. Could solve and then multiply everything by negative 1. But I'm just going to choose to add a to both sides. Add a. So on the left, that's going to leave us with a minus 2 equals, on the right, we've got negative 6. Last step here, almost there, solving for a. Right now it has 2 being subtracted from it. So let's add 2 to both sides. And a must be negative 4. Hey, just like we predicted, right? Well, maybe not the 4, but the negative, right? We predicted that a would be negative because it looks like a reflection has occurred here. Again, comparing to y equals 1 over x, it's positive on the wrong intervals, right? Y equals 1 over x is supposed to be positive when x is greater than the vertical asymptote, and negative when x is less than the vertical asymptote. Obviously, that's not 100% true, but I mean like have this kind of shape when x is above the vertical asymptote, and this kind of shape when x is below, and it's been flipped, right? So like we kind of predicted, a reflection has occurred. A is negative. So that means putting it all together, our equation is y equals a, we now know, is -4, x minus h, we know h is 1, plus k, and we know k is -6. And there we go. That is the equation for this rational function. It's y equals -4 over x minus 1 minus 6. If you put that into your graphing calculator, you will see something that looks exactly like this. And we got it all just by thinking about, okay, how is this kind of like y equals 1 over x, but having been messed with, right? So it's a very powerful thing to be able to do, to compare how your graph looks now compared to what we would expect it to look like if it were just y equals 1 over x. That's the power of having a base graph to compare back to. Okay, so now's a good time to go ahead and try some practice here. You can pause the video for a bit. At the very least, try this one right now while it's fresh in your brain. And then, you know, as always, feel free, if you C goes so-so and you want to try some more, maybe do D or B or A for this same one. But it's giving you the graph, and it wants you to write the equation for the function in the form y equals a over x minus h plus k. Okay, so try that one out, and then when you come back, we'll finally talk about the ones I've been referring to where they actually can't really, or at least it doesn't really make sense to write them in that form. All right, so let's go a little bit deeper now with our rational functions, okay? Because remember, what's a rational function? It's a function where the equation involves a polynomial over another polynomial, right? It's a fraction, a ratio. That's why we call them rational functions. The root word there is ratio, right? And so far we've kind of been thinking about this base one here, okay? But a lot of rational functions aren't really going to like fit well into that mold, right? Like we could have something like y equals x squared plus x minus 4 over 2x plus 8, right? I mean, that's possible, just making that up there. And for a lot of rational functions, we can say it's going to look a lot like the graph of 1 over x, but having been messed with. But something like this is not really going to. Something like this, it can be possible to use polynomial long division to like actually divide these to get something that looks like this. But honestly, that's often not really necessary. And there really are cases where it just can't even be done at all, right? So just to show you what I mean here, right, here's y equals 1 over x. And some fit nicely, some look like the graph of 1 over x, but having been transformed a lot. Whenever we've got like this one, like a 2 over an x minus 3 plus 4, you can see what I mean. That does look a lot like 1 over x if we just moved 1 over x, maybe stretched it. They've generally got kind of the same shape there, right? But what about something like this, which is still a rational function? It's still a polynomial over a polynomial, right? That is the graph of a rational function. You can see, though, that really doesn't look like this. It's not of the same form, right? So while it is possible with many to like do some long division and get it into a similar form, again, like I said, it's often not necessary, and we can do all the analysis we need to do anyway without doing that, right? Or, you know, something like this, that doesn't really look like y equals 1 over x, right? We could come up all day with polynomial functions that don't quite look the same way. So while this is a good base graph to think about many rational functions, okay, it falls short for lots of these. There's no way to take y equals 1 over x and stretch it and translate it and make it look like that thing or that thing. So that's what we're going to talk about next here. We're going to talk about those graphs that don't quite fit into that form. Okay? Now, it can be possible to take some of those rational functions and actually use polynomial division to write them in the form y equals a over x minus h plus k. We actually just do regular polynomial division, and when we write the division statement for many of those polynomial functions that might not originally be in this form, when we write the division statement, it can end up looking like that form. That's great. We can totally do it. But honestly, it's not really necessary. We can do most of the analysis we want with it in its original form. In fact, it's kind of easier to do that often. And sometimes it really isn't possible. You can't get there with just polynomial long division. They just look too different. So remember, rational functions have polynomials as their numerators and their denominators. Because we're dividing by a polynomial, we can have non-permissible values. Those are values of x that would make the denominator 0. That's why they're non-permissible, because we'd be dividing by 0, which is not allowed. So this is what I referred to earlier in the lesson. We saw that NPVs can cause a vertical asymptote on a graph, right? And they totally can, and up until now, that's all they've caused. But they actually can cause something else, what we call a point of discontinuity. Okay, what is a point of discontinuity? We'll get into it here in a second, but the brief definition is it's just one point that's kind of discontinuous. It's a single point that our graph doesn't pass through, but it doesn't actually influence the overall shape of the graph. It's just one point where the graph is undefined. To get into why this is the case, let's take a look here. Okay, so consider the following rational function in which the numerator and the denominator have been given to us in factored form. That's nice of them to do, but it is just a rational function. This is a polynomial, it's just been factored. And so is this, it's just been factored. And so it's asking us, what are the NPVs, the non-permissible values for this function? Well, we're not allowed to divide by 0, right? So I see two ways where we could be dividing by 0, right? If x minus 1 were 0, or if x minus 3 were 0. So that means x minus 1 is not allowed to equal 0, and therefore x cannot equal 1. That's one non-permissible value. If x is 1, I'm dividing by 0, okay? But also, x minus 3 is not allowed to equal 0, and therefore x is not allowed to equal 3, right? Two NPVs. X cannot be 1, x cannot be 3. Either one of those would have me dividing by 0, right? 0 times anything is 0. So if one of these is 0, the whole denominator is 0. But you might be noticing something, that we can do a little bit of simplification to this equation. Now again, don't forget, this is where we're starting from, and we are not allowed to make x 1 or 3, because then our equation we would be dividing by 0. However, we can simplify this equation a bit because we have x minus 1 over x minus 1. Which is just 1, right? Anything divided by itself is just 1. So x minus 1 over x minus 1 is just 1. We can kind of cancel those out, we sometimes say. Meaning that, really, okay, this is pretty much mathematically equivalent to this, right? This is just equal to 1 anyway. So y equals x minus 1, x plus 2 over x minus 1, x minus 3 is essentially the same. Now notice I'm saying essentially, not exactly, the same as y equals x plus 2 over x minus 3, right? They're basically equivalent. These are basically equivalent, or close to equivalent anyway. Their graphs will therefore, right, the graphs of y equals x minus 1, x plus 2 over x minus 1, x minus 3, and y equals x plus 2 over x minus 3. These are very close to just being the same equation, because x minus 1 over x minus 1 is just 1. We'll look, so those two graphs, since they have almost the same equation, will look almost identical. Almost. They are going to have a very key difference. So look, sure enough, here are the graphs of each function. They look very similar, but there is one key difference, okay? And this is pulled straight out here from graphing them with technology. Here is the graph. Here is the graph you will get if you type in what we actually were thinking about to start with. Y equals x minus 1, x plus 2 over x minus 1, x minus 3. Here is the graph you will get if you just plug in our simplified version, y equals x plus 2 over x minus 3. Zooming out, they do look very, 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 very similar. Their general behavior, big picture here, is basically identical, right? Look, compare points even, right? Like you can see the points this has, the points this has, the shape it has, the shape it has, the asymptotes it has, the same asymptotes this one has. But there's a very, very important difference between the two. This one, when you look at the value of the graph when x is 1, it's undefined because we'd be dividing by 0. right? You can't divide by 0. So there's a little hole in our graph there. That is purposely drawn. It's not filled in, right? It's not filled in like that, showing that it's part of the graph. It's left empty. That indicates that there's a little hole in our graph. It's a single point where the graph is undefined. Overall, the shape of it does look like this one, but there is one point that's basically missing, okay? And that's the point where x equals 1. So even though this simplifies out of the equation, and overall it looks a lot like x plus 2 over x minus 3, we can't lose sight of the fact that x was still not allowed to be 1 because it does still make this equation undefined. I would be dividing by 0, right? Over here, if we were acting like this really was our equation the whole time, right? Nothing wrong with simplifying, but if we forget that this isn't actually the equation we started with, we'll see that it's totally fine for x to be 1. There's no hole here, right? There's where x is 1 and y just ends up being negative 1.5. 1 plus 2 is 3. 1 minus 3 is negative 2, so 3 over negative 2 is negative 1.5, right? And there's no hole there. It is filled in. So this is the idea behind a point of discontinuity, where y equals x minus 1, x plus 2 over x minus 1, x minus 3 had a non-permissible value. There is now a point of discontinuity. I shouldn't say just where it had a non-permissible value, but specifically of x equals 1, because that's the one that kind of got canceled out, right? We lost it in the simplification. It's a literal hole in the graph at which the function is undefined. And again, it makes sense when we think about it. We kind of talked this through, but let's really break it down here with the notes. Y equals x minus 1, x plus 2 over x minus 1, x minus 3. It can be simplified to y equals x plus 2 over x minus 3. So whenever you can simplify something, that means it's, essentially equivalent. You might lose some information that we have to keep track of, but if we can simplify it from one to the other, we're not changing what it is, we're just simplifying. So overall, their graph should have the same general shape, right? We really can write this in a way that's not like mathematically wrong as this. So their graph should be about the same. But x still cannot be 0 in what we started with, or we'd be dividing by 0. So even though that factor cancels out mathematically, the NPV associated with it is still retained. That, just because it can simplify out, doesn't change the fact that if x really were 1, we'd be dividing by 0. Okay? But again, it's not actually like overall the equation is pretty close to being the same as this. And so we wouldn't expect it to like change the entire behavior of the graph, right? We wouldn't expect there to be an asymptote at x equals 1, because that would really change a lot about how our graph looks. Like it couldn't be here, it would be instead approaching there, right? And we know this one would never do it. That one, there's no reason for that to have an asymptote at x equals 1. And this is more or less the same equation as this. It just has one more point that's defined than this one, right? So we wouldn't expect like an asymptote where it's actually going to like really govern the overall behavior of the graph. We just kind of have a hole in our graph, a little spot where it's undefined. We wouldn't expect an actual asymptote there, just a single point of discontinuity is on the graph, because everywhere else, it really is identical to y equals x plus 2 over x minus 3. It's just that one point where things turn out a little bit differently, because here we'd be dividing by 0 if x were 1, here we're not, okay? And then, once we've got it simplified, we can find the y coordinate like I did here. You might be saying, how am I ever supposed to find the y coordinate of the point of discontinuity if I'm not given the graph? Well, that's where the simplified one can help you out, right? If you take the simplified one, plug in the x coordinate of your point of discontinuity, that will give you the y coordinate of that point of discontinuity. I should add here into the simplified function. Because if you plug it into the regular function, you're going to get undefined, right? If I put x equals 1 into this, it's going to be undefined. But if I want to know, okay, I know that this is like this, so what's y when x is 1 for this? We get negative 1.5, and that tells us the y coordinate of our point of discontinuity. So to briefly summarize, if a factor appears in the numerator only, this is going to tell us the location of an x-intercept. Okay, now that makes sense Because if we have, y equals, let's say, x plus 3 over x minus 2, okay? How do I make this equal 0? Well, to make any fraction equal 0, I have to make its numerator 0, right? So this tells me that y will equal 0 when x equals negative 3, right? I don't know why I'm making up an example. There's literally an example right here in the notes, okay? Just for an example here, if y equals x plus 2 over x minus 3, when x is negative 2, that's the 0 associated with that factor there, y equals 0, right? The value of x that makes y 0, that's just the definition of the x-intercept, because I'll have 0 over, doesn't matter, it's equal to 0. So x equals negative 2 is an x-intercept. So a factor that's only in the numerator tells us about where an x-intercept could be. If a factor appears in the denominator only, that's going to tell us about the location of a vertical asymptote, right? It's really going to govern the overall behavior of the graph. It's a NPV that the graph can never actually reach, but it will approach, right? Not just a hole, but an actual asymptote that gets approached by the overall graph. So for example, in the same one, y equals x plus 2 over x minus 3, we can see that when x equals 3, y is undefined, and it gets very close to infinity as x gets closer to 3, right? It's not like that x minus 3 is canceling out. That really is part of our equation. No way to simplify it out. And if a factor appears in both the numerator and the denominator, and then it cancels out completely when simplifying, it just tells us the location of a point of discontinuity. Because again, x really can't equal 1 here. But if we simplify this equation, it's going to look a lot like this everywhere else. There's just going to be that hole at x equals 1 that's left over, so to speak, from when we hadn't simplified yet. Okay, so for this one, we can see that the graph will generally look like x plus 2 over x minus 3, except that x can't equal 1, right? It's going to look exactly like this, except it's going to have the special rule that x will never equal 1, okay? Let's try this out a bit here. I like these. They're kind of fun. So it wants us to complete the table and then match each function with its graph. So our first step here is to factor each equation. You might recall from Math 20, whenever you're dealing with these rationals, right? We haven't had to think about it yet because we've been doing the a over x minus h plus k type. But now that we're dealing with real, true, multi-term polynomials in our numerator and or denominator, you might recall from Math 20 that whenever dealing with rational equations, expressions, functions, whatever, your life gets a million times easier if you factor, right? Imagine if this was all, foiled back out and we didn't have it factored. We'd never notice that x minus 1 canceled out because we wouldn't have those two factors being multiplied together, right? We wouldn't have x minus 1 times something over x minus 1 times something. So we need to factor first in order to make this, really to make it possible in the first place, but definitely to make it a lot easier. So let's factor this first. Numerator, can't do much with that. X minus 1, there's no factoring that, right? No greatest common factor, anything we could do there. But here, x squared minus 1, do you recognize this? This is actually a special type of polynomial. This is what we call remember, difference of squares. It's a perfect square minus difference, a perfect square. Hence, difference of squares. Okay, x squared is just, x squared. And 1 is a perfect square. It's 1 squared. So whenever we have a difference of squares, it's always going to factor 2. If we have I'll just say if we have m squared minus n squared, it always factors to m plus n times m minus n, right? For reasons that in the interest of time I won't get into. I've talked about it in earlier lessons and Math 10 review, but if you FOIL this out, you'll see that you always just end up with m squared minus n squared. And that's why we can be confident that these differences of squares factor to that. You could also use product sum method. You could ask yourself what two numbers multiply to -1 and add to 0. The answer is 1 and -1. I'm going to use the difference of squares stuff here. So I'll say y equals x minus 1 over x squared minus 1. That's just x plus 1 times x minus 1, right? Square root of the first thing plus the square root of the second thing times the square root of the first thing minus the square root of the second thing is how we factor a difference of squares. All right. Now, can this be simplified at all? Well, we've got x minus 1 over x minus 1. Now, remember, we're not going to forget about this x minus 1 in the denominator, but we can see that this is overall essentially equivalent to x minus 1 over x minus 1 is just 1, so this is just 1 over x plus 1. Now again, they're not exactly the same thing because x can be 1 in this, x cannot be 1 in our true equation. But it does simplify to that. So overall, the graph of this, or the graph of this, is going to look exactly like the graph of this with one key difference. This one's going to have a hole, a point of discontinuity, where x is 1. Okay, let's not spoil the fun though, we'll get to that in a minute. So what are the non-permissible values? Well, we're dividing by x plus 1, so x cannot equal negative 1. And we're dividing by x minus 1, so x cannot equal 1, right? So x cannot equal 1, x cannot equal negative 1. Otherwise, we're dividing by 0. Now, here's where we got to think about it, okay? Our vertical asymptote. Remember, where are these going to appear? Vertical asymptotes are like part of the overall behavior of the graph, right? The graph, it's a major kind of feature of how the graph behaves, right? So it's not something that's going to be simplified out and not really show up in the simplified form of the equation, right? It should still be there. So our vertical asymptote is going to be at x equals negative 1, right? Another way to think about it is from factors that appear in only the denominator. They're not getting simplified out. And don't cancel. They are part of the equation even after simplifying, and therefore they influence the overall shape of the graph, giving us that vertical asymptote. Okay, point of discontinuity. Now this is just a hole in the graph, right? It's not changing the overall shape of the graph, but there's still the fact that x cannot equal it. Do you see something that might be like that here? Right, x equals 1. X cannot equal 1, okay? But that doesn't change the overall shape of the graph because big picture, it simplifies out and it cancels out. So the overall shape of the graph is going to look a lot like 1 over x plus 1, and that graph can go through x equaling 1. There's just going to be a hole there because of the fact that we know really x cannot equal 1 because this is what we started with, right? Or this is what we started with. If x is 1, we have 1 squared minus 1, which is 0. So we have a point of discontinuity at x equals 1, okay? Let me give myself a little more room there. I'll say POD when x equals 1. Now it's a point, so it has an x coordinate and a y coordinate. How are we going to get the y coordinate? Well, we can't put x equals 1 into this equation. It just gives us something undefined. But we can figure out, generally, what would y be on this graph when x is 1, right? By using the simplified version, where we can actually make x 1. So that's how we can get the y coordinate of a point of discontinuity. So we'll use the simplified equation. Y equals 1 over x plus 1. So what is that? What is y when x is 1? Well, it's 1 over 1 plus 1, which is 1 over 2, which is 0.5. So our point of discontinuity is at 1, 0.5, right? 1, 0.5. Let me just shrink that a bit. I should have given myself a little more room. That's tiny, but gonna have to be. So our POD is at 0, sorry, not 0, 1, 1.5. Okay, and again, another way to kind of think about this, I don't want us to get too much into robot mode and not thinking about why that makes sense, but these will come from factors that appear in numerator and the denominator and end up canceling out, right? Because again, they don't influence the overall shape, but they do leave behind a little hole still showing us that, hey, even though I simplify out, x still can't be 1 or you're dividing by 0. Okay. Then it wants us to pick the matching graph below. How about we do all three of these and then we'll worry about matching after. Kind of fun to do it that way. Okay, let's do this one. Y equals x squared plus 2 over x squared minus x minus 2. Well, that numerator I don't think can actually be factored, right? Nothing, this isn't a difference of squares. It's only got 2 terms. Nothing multiplies to 2 and adds to 0 is another way to think about that. Our denominator, though, certainly could be factored. Remember, whenever working with these rational functions, you want to factor the numerator, factor the denominator, so that things are easier to work with, right? And just one at a time. Sometimes students I find get overwhelmed with these. They say, how do I factor this thing? Just zoom in one at a time. Can you factor the numerator? No? Okay. Can you factor this denominator? That, I think we have some hope. We could probably just use some product sum. It's just a good old trinomial where our leading coefficient is 1. So we could just do something that multiplies to negative 2 and adds to negative 1. So multiplies to negative 2 and adds to negative 1. Well, how about negative 2 and positive 1? Right? So our factors then for our denominator could be, we could rewrite this equation as y equals x squared plus 2. Again, not really much we can do there, but our denominator we said we could factor as x, it was negative 2 and positive 1, so x minus 2, x plus 1. Okay. Now, if we look here, can we do any simplification? Not really, right? Be careful. X squared plus 2 can't cancel with an x minus 2. They're not the same thing, right? This is an x squared. This is an x. And this can't be factored. So I actually don't think we can do any simplification here. So that's just our equation. We factored it. So we did our due diligence to check if there was simplification we could do, but it doesn't look like there actually is. So what are our non-permissible values? Well, we can't divide by 0. So from this factor, we see that x cannot equal 2. And we can't divide by 0. So from this factor, we see that x cannot equal negative 1. Our vertical asymptotes. Okay, again, we have 2 factors in our denominator that aren't going anywhere. They're not getting simplified out. Those are both going to give us vertical asymptotes, right? X can approach 2, but never reach 2. X can approach negative 1, but never reach negative 1, right? So our vertical asymptotes are at x equals 2 and x equals negative 1. We're going to get 2 there, right? Another way to think of it, factors that appear in the denominator and don't cancel out. Denominator only, I should say, and don't cancel out, right? These don't cancel out and they only appear in the denominator. So that's going to give us those vertical asymptotes. Point of discontinuity. Those are factors that, are in our denominator, but they can technically be simplified out. Factors that appear in both the denominator and the numerator, therefore, right? So that they could be canceled out. Do you see anything like that here? I don't. I don't see any factors that appear in our numerator and denominator and could therefore be canceled out. So our PODs, I don't think we have any. None. There's no points of discontinuity. There's no factors that end up canceling out because they appear in both the numerator and the denominator. So when we get to that one, we're looking for something that has 2 vertical asymptotes and no points of discontinuity. I can already kind of have a pretty good idea of what that one might be, but let's leave it for now. Let's not spoil the fun. Okay, last one here before we match the actual graphs. We've got y equals x squared minus 5x plus 6 over 3 minus x. As always with rational functions, your first step should be to factor the numerator if possible and factor the denominator if possible. Denominator, I don't think we can do much, but numerator, that looks like it's worth a shot. It's a regular trinomial with an a value of 1, so we might as well give the product sum a chance. We need 2 numbers that multiply to 6, add to negative 5. How about negative 3 and negative 2? That seems like pretty promising. Negative 3 times negative 2 is 6. Negative 3 plus negative 2 is negative 5. So we've got, in our numerator, x minus 3 times x minus 2 over 3 minus x. All right, now can we do any simplification here? We actually can. It's a little tricky because x minus 3 and 3 minus x, those are like different. That's definitely true. But one is actually just kind of the negative of each other, right? A positive x, a negative 3, a positive 3, a negative x. So we could look at it this way. What if I factor a negative 1 out? Almost, right? What if I factor a negative 1 out of this thing? Well, I'd be left with negative x plus 3. Or in other words, positive 3 minus x. Oh boy, I'm going to run into the next space a little bit here. Apologies. Over 3 minus x, right? And now we can see, aha, so these actually do cancel out, right? You could even notice it here and say that's just negative 1 instead of being 1. But that gives us a simplified version of this equation as being negative 1 times x minus 2, or negative x minus 2 over 1, or negative x minus 2. Or if you really want to keep going with it, you could even say negative x plus 2, or 2 minus x, right? Distributing that negative. Okay, that is our factored and then simplified equation. Okay, what are our non-permissible values? Always go back to before you simplify to find the non-permissible values, right? This has no non-permissible values at all. But we know that our actual equation does have an NPV. It's that x cannot equal 3, right? Because we'd have 3 minus 3, which is 0 in our denominator, and that's not allowed. Now the vertical asymptote, remember, those are factors that appear in the denominator only and don't get canceled out. Well, this didn't appear in the denominator only, and it did get canceled out, right? It appears in the numerator and the denominator. So is this going to have a vertical asymptote? It is not. You're right. No vertical asymptote. Because when all is said and done, what does this end up actually looking like? It ends up looking like the graph of y equals 2 minus x, which would not have a vertical asymptote, right? It is going to have a point of discontinuity. We know there are values of x that are forbidden, but they're not the type of value of x that the graph approaches and influences the overall shape of. It's just a hole. It's just a holdover from the fact that we are dividing by 3 minus x, so x can't equal 3, right? But that just ends up simplifying out, and we end up with, overall, mostly, it looks like the graph of y equals 2 minus x, with the only exception being that x can't equal 3 for our graph. So the point of discontinuity is going to be at x equals 3. Well, here, let me write it out. That's the x-coordinate of our point of discontinuity anyway. POD when x equals 3. What's the y-coordinate? We can use the simplified equation to tell us that. So our simplified equation just ended up being 2 minus x. So this is just going to be 2 minus 3, or negative 1. So our POD is at, oh boy, really running out of room here. When x is 3, y will be negative 1. Whoops. Okay, and now let's match each graph. Okay, so graph 1, what does it match? Well, graph 1 I see, okay, I'm noticing a point of discontinuity at x is 1, y is about 0.5. I'm noticing a vertical asymptote. Looks like our vertical asymptote is at x equals negative 1. Right? Vertical asymptote at x equals negative 1. Okay. With a point of discontinuity at like 1, I feel pretty good about saying that's at 0.5 for the y-coordinate. Whoops, not 0, 1, 1.5. What does that match? Which of these does it match? Well, hey, vertical asymptote at x equals negative 1. That doesn't necessarily eliminate this one, except it kind of does because it's supposed to also have a vertical asymptote at x equals 2. It eliminates this one. Look, vertical asymptote at x equals negative 1 and a point of discontinuity at 1, 1.5. I think this first row here, that matches graph 1. Okay. What about this graph? I see, how many vertical asymptotes do you see? I actually see 2. So right away we can kind of tell what this should be. But it looks like there's a value of x that the graph is approaching there, and there's a different value of x that the graph is approaching here, right? Looks like one's at x equals 2, and one is at x equals -1. Well, there we go. That kind of tells us it must be this one, right? Also, no points of discontinuity. There's no holes in this graph. It does have vertical asymptotes and therefore NPVs, but those NPVs aren't simplifying out of the equation so that they just end up as little holes. They're there in the equation even after simplifying, and they influence the overall shape of the graph. So I think graph 2 matches that one. And then yes, by process of elimination, graph 3 must be that one. But taking a look, does it check out? Does it have no vertical asymptote? No, it doesn't, right? Does it look like a lot like the equation y equals 2 minus x? Or y equals -x plus 2? So does it look like a line with a slope of -1 and a y-intercept of +2? Yeah, it definitely does. The only difference from this graph and the graph of y equals -x plus 2 is that this one has a hole. This one has a point of discontinuity when x is 3. Well, hey, that's exactly what we predicted. When x was 3, y would be -1, and we'd have a point of discontinuity. And no vertical asymptote, because once simplifying out, there's actually no factor that's in our denominator, right? So that checks out. Okay, let's reverse this now. We looked at having the equation and matching it to a graph. Let's see if we can have a graph and write an equation from it. Now, in order to do that, it's the exact same thought process. It's just reversed, right? Everything that our equation told us about the graph can tell us about the equation. We just have to remember, right? An x-intercept tells you that the associated factor appears in the numerator only, right? So for example, an x-intercept at n tells you that the numerator contains a factor x minus n, because when x is n, the numerator becomes 0, and therefore overall the function's, its y value becomes 0. Well, when y is 0, you've got an x-intercept. A vertical asymptote tells you that the associated factor appears in the denominator only. Again, denominator only because it didn't get canceled out. It really is influencing the overall shape of the graph. X can approach that value but never reach it. So a vertical asymptote on our graph at x equals n tells us that the denominator contains a factor x minus n, and the numerator doesn't contain that factor, so they don't cancel out. A point of discontinuity tells us that the associated factor appears in both the numerator and the denominator and actually fully cancels out. Okay, so a point of discontinuity at x equals n tells us that the numerator and denominator each contain a factor x minus n. And we use this to just build the equation, right? Like we could say, all right, what's going to be in our equation? Well, it might have like an x minus n up here because there's an x-intercept at n. And it must have a x minus p down here because there's a vertical asymptote at p. And it must have, you know, an x plus m and an x plus m because there is a point of discontinuity when x is -m, right? That kind of thing. Look at that. Just by looking at those things, those vertical asymptotes, x-intercepts, and points of discontinuity, we've got a lot of our equation put together. The only thing is, none of that changes, right? This is still an x-intercept. This is still a point of discontinuity. And this is still going to tell me a vertical asymptote if I put a 3 here, or a -7, or a positive 127, right? Whoopsies. So my point there is that alone isn't actually enough to definitively determine the equation of the graph because there could still be some value of a here. So we'll just put in an a there, what it's being multiplied, and then, like we so often do, we can use any point to determine the value of a, right? We will have all of this stuff just from the x-intercepts, the vertical asymptote, and the point of discontinuity, and that's most of the equation. We'll have numbers in there based on where the graph actually has those features. And then if we can find any point, we can put in its x and its y, and we know the equation is supposed to be true. So we can put in the y and the x and figure out what a must be in order to actually make that equation true. So like I say here, the y-intercept is often a good choice just because it makes the math nice when x is 0. Not mandatory, and if it's a, ugly y-intercept that's kind of hard to estimate, then don't use it. But just a pointer. If you can see the y-intercept, it's a nice number. It is kind of a nice one to do. Okay, and again, like I just said, we need to consider the possibility of an A because none of the above features would actually be changed if the factors were all multiplied by some constant A. So those alone are not enough to definitively determine the equation because there could be some A and it would still have all of those features. So determine the equation of each graph function. Let's put this into action here. What do we see? What do we see? Well, I see a couple things. Right off the bat, I see a point of discontinuity. Point of discontinuity at 1, 3. Okay, so when x is 1, this graph is undefined, right? X cannot equal 1. Well, let's start building our equation right off the bat. I'm going to leave room for there to be some a value, okay, because there could be some a value, but if there's a point of discontinuity when x is 1, what's the associated factor? It's x minus 1. And where does it appear? In the numerator and denominator. You've got it, right? X minus 1, because it's just a point of discontinuity. It's not an asymptote. So that must simplify out of the equation if we were to simplify it, okay? All right, points of discontinuity tell us that a factor appears in the numerator and the denominator. There we go. What about this x-intercept here? I see an x-intercept at -2. So what's the associated factor, first of all? It's x plus 2, you've got it. And where does it need to appear? In the numerator only, right? Because, right, if y is 0 when x is -2, then that means our numerator must become 0 when x is -2. 0 over doesn't matter, it's equal to 0, okay? And there we go. I don't see a vertical asymptote, so there's nothing to throw into just the denominator, and I don't see any other x-intercepts or points of discontinuity, so there's really no other factors to consider here either. Just going to make that look a little less weird. There we go. And so all that's left to finish off this equation would be the value of a, right? Now, how can we get the value of a? Well, we've got y's and x's. We've got a whole bunch of them on this graph that are supposed to satisfy this equation. I've got everything else in place. Let me just pick a y and pick an x, pick a point, in other words, and see if I can use that to figure out what a must be to make this equation true. Because again, every point on the graph should make this equation true. That's why it's on the graph. Whoa, 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 what's happening there? Okay, so you can call it step 2 if you like. Let's actually figure out what a is. So pick a point, any point. Like I said, the y-intercept's nice often. Like if you can see the y-intercept clearly, then it's a good one to go with because it just sticks out, right? It really sticks out. So 0, 2, and the other reason it's nice, the reason it's nice is that it makes x 0, and that just makes the math easy. But in this case, since our y-intercept is easily seen, it's at 0, 2, that's just a point on our graph, we can use it, right? If it was something weird like this where we'd have to estimate what the value of it was, we probably wouldn't use it there, but here it is. It's just 0, 2, so let's use it. So a point on our graph is that when y is 2, we've got our a times our x minus 1. Well, now we know that's 2 minus 1. Okay, when y is 2, 0 minus 1. X is 0. 0 minus 1 times x plus 2, so 0 plus 2, over x minus 1, so 0 minus 1. So we're on our way to figuring out what a is. I'm just going to drop the color coding here now. So 2 must be equal to a times, 0 minus 1 is -1 times 2. Over 0 minus 1 is -1. So 2 is equal to 2a divide both sides by 2, and a just must equal 1. By the way, we could have canceled this out at the beginning if we wanted. 0 minus 1 over 0 minus 1 is just 1, but leaving it in there on this one. So that means y equals, right, put it all together. All we didn't know was the value of a. Well, now we know that a is just 1, so we can even just leave it out. 1 times anything is not going to change it. So x minus 1, x plus 2 over x minus 1. Again, we figured out that x minus 1 had to appear in both the numerator and denominator because it had a point of discontinuity when x was 1, right? We figured out that x plus 2 had to appear in just the numerator and not cancel out because it had an x-intercept when x was negative 2, right? And that gave us most of the equation. All that was left to do was figure out what a had to be, and we did that just by plugging in any point we could see. X, y. I chose to use the y-intercept because it was easy to see, and the y-intercept is nice because x is 0 there, so it makes the math a little simple. All right, what about this one? What do we see? Well, right off the bat, I see 2 vertical asymptotes, right? That might be a good starting point. Vertical asymptote at x equals negative 1. Vertical asymptote at x equals 3. Okay, let's start building our equation. Why waste any time with it, right? These tell me, right, if we have a vertical asymptote, the denominator only, it doesn't cancel out, so the denominator only contains the associated factors with those. So I'm going to leave room for there to be an a, because again, that wouldn't change any of the stuff we're going to talk about here. But now I know that my denominator, if x equals negative 1 gives us a vertical asymptote, then the denominator must contain a factor x plus 1, because if x is negative 1, that becomes 0, and we're dividing by 0. And if we have a vertical asymptote at x equals 3, then the denominator must contain a factor x minus 3, because when x is 3, we're dividing by 0 then, okay? And denominator only, because it is a vertical asymptote. It really is influencing the overall shape of the graph. It's not just a point, a hole, okay? Speaking of points and holes, I see a point of discontinuity. POD when x is, what is that? That's 1, when x is 1. So what does that tell me? Well, that tells me my numerator and denominator contain a factor of x minus 1. X minus 1, right? Because again, x really can't equal 1, but that factor is going to cancel out in the overall equation. So mostly the graph just looks like when these factors have canceled out, with the exception that there's that hole, okay? And the last thing to look for is x-intercepts. I do see an x-intercept here, right there. X-intercept when x is negative 2, right? Meaning that y is 0 when x is negative 2. Well, that tells us that our numerator, and only our numerator, must contain a factor of x plus 2. Because then when x is negative 2, this is 0, and my numerator is 0. I have 0 over whatever, doesn't matter, it's all 0. So y will be 0 when x is negative 2, which is what the graph shows us. And that's most of the battle. Look how much of the equation we have already. We've got like almost all of it. It's just a. How can we get a? Pick a point. Once again, our y-intercept is nice and easy to see, so I'm going to use that one. So it looks like our y-intercept is at 0, negative 2. And again, just makes the math nice when x is 0. So step 2, now we're going to find a. We got most of our equation from the x-intercepts, the vertical asymptotes, and the point of discontinuity. All that's left is the a value. So negative 2 will be equal to whatever a is. And when y is negative 2, x is 0. So we've got 0 minus 1 times 0 plus 2 over 0 plus 1 times 0 minus 3 times 0 minus 1. So negative 2 is going to be whatever a is times negative 1 times 2 over 1 times negative 3 times negative 1. I mean, we could have done this earlier, but we can cancel out those negative 1s. So negative 2 is a times 2 over negative 3. 1 times negative 3. Okay. And so now, if we multiply both sides by negative 3 to get rid of that, we get that positive 6 equals a times 2. So positive 6 equals 2a. Divide both sides by 2. 6 over 2 is 3. So a is 3. And there we go. Remember, that was all we were missing. So we can write the equation. Y must equal 3 times, we can even put that 3 up in the numerator. You'll often see it done that way. 3 times x minus 1 times x plus 2 over x plus 1 times x minus 3 times x minus 1. And there we go. There's the equation. Again, I just decided to put the 3 up there for that one. You could definitely have left the 3 there. Just looks a little cleaner, I think, when we put it up there. Remember, this is the same as, 3 over 1 times all that stuff. That's why I'm able to just put the 3 up in the numerator if I want to. All right. So, summarizing, right? What did we do? We used the x-intercepts to tell us what factor or factors must appear in the numerator and only the numerator. We used the vertical asymptote to tell us what factor or factors must appear in the denominator only. And then we used any points of discontinuity to tell us what factors appear in both the numerator and the denominator and would therefore get canceled out when simplifying. And then all that's left to do, you're going to have most of the equation after doing that. You've just got to find a by plugging in any xy point. So go ahead, see if you can apply that logic here to this one. And again, as always, if you're feeling like you could do a little more practice right now, that's never a bad idea. You can take a little pause, do some practice, take a little break from my voice, and try more out, right? If you do A and you're thirsty for more, try B, C, D. And then when you come back, all we got to do is a diploma question, and then there's just some notes talking about horizontal asymptotes. It's nothing really new, but just circling back to it for these ones that are not in that form, a over x minus h plus k. So try that one out. All right, so let's dive into this diploma one here. So this is from an old diploma, 2019, I believe. The vertical asymptote of the graph of the rational function. So we're looking, there's a vertical asymptote involved. Y equals all that, x squared minus 3x minus 10 over 4x squared minus x minus 18 is defined by the equation x equals k. So we're looking for the equation of the vertical asymptote, right? Where is the vertical asymptote? At what value of x? The value of k to the nearest hundredth is blank. So yeah, we're looking for where is the vertical asymptote? At x equals what? Okay, well, how could we figure that out? Well, if we were to factor this thing, then we would be able to see, right? We'd be able to see, are there any factors that appear in the denominator only? Because those factors give us a vertical asymptote, right? So let's get to work, right? I mean, like always with rational functions or rational expressions or rational equations from Math 20, it's never a bad idea to factor. In fact, that's often kind of the first thing you need to do to be able to really start these. So first, we're going to factor numerator and denominator separately, but like we'll factor the numerator and then we'll factor the denominator. We've got y equals x squared minus 3x minus 10 over 4x squared minus x minus 18. So let's just circle in on them one at a time, focus in. We're going to factor this thing, and then we're going to factor this thing. Okay, let me do the numerator first. Numerator looks a little bit easier because that's a value of 1. It's a regular trinomial with an a value of 1, right? A leading coefficient of 1. So I can just use product sum, meaning that I just need to think of two numbers that multiply to the constant, the c term, so negative 10, and add to the x term, so negative 3. multiplies to negative 10, adds to negative 3. How about negative 5 and positive 2? That would work, right? Negative 5 times 2 is negative 10. Negative 5 plus 2 is negative 3. So we can factor this numerator, this x squared minus 3x minus 10. It really just equals x minus 5 x plus 2. Done. Numerator factored. Okay. What about our denominator now? Let's focus in on that denominator. So we did that. Okay, numerator, product, sum. Let's now focus in on this denominator. How are we going to factor that? Well, be careful. We can't use product sum here. Do you remember why? Denominator. Do you remember why we can't use product sum for this? Because our a value isn't 1. It's 4, right? It's not as simple as just what number multiplies to this and adds to this. We need to ask ourselves first we need to use decomposition because our a value is not 1. Let me finish writing that before I move on to my next thought. We need to ask ourselves what multiplies to a times c, right? So AC in this case is 4 times negative 18, which is negative 72. So we need two numbers that multiply to negative 72 and add to negative 1. All right, and when in doubt, don't forget you can always just start listing the factors of 72. But one that comes to mind for me, 72 is 9 times 8. And hey, 9 and 8 are separated by 1. So if we did negative 9 and positive 8, that would work pretty well, right? Negative 9 and positive 8. That would equal negative 72 multiplied and negative 1 when added. So now this is decomposition, so that's not it. Like, we're not done now and we just write our two factors. We actually have to do the decomposition part, right? So we got to say this is, our denominator is 4x squared, and here's where we decompose. We're going to break that negative x into two terms with these as those two coefficients. It'll be 4x squared minus 9x plus 8x. If there were a minus there, remember, we'd have to be careful not to put it there. We'd have to rewrite it as plus negative 8x, but there's not. That's why I chose to put the minus 9x there, so we're safe. Plus 8x minus 18. And now we're just factoring by decomposition. So I group the first two terms. I'm going to group these two. And I group the second two terms. See what I mean? We're safe. We're not changing what this means because there's no negative there. We still really are adding the 8x and subtracting the 18. And then we factor those two groups individually. So we pull the greatest common factor out of each. So what's the biggest thing that both of these are divisible by? I think just x, right? I think our greatest common factor for this is x. So I'll pull an x out as a common factor here. 4x squared divided by x is just 4x. Negative 9x divided by x is just negative 9. And then over here, 8x and negative 18, 2, I think, is the greatest common factor there, right? That's the biggest thing that both of those are divisible by. So I'll pull out a 2. That's going to leave me with 8x over 2 is 4x. Negative 18 over 2 is negative 9. And hey, remember, if we did it right, these should always be the same thing. They actually need to be the same thing or we can't continue on with our solution, because the next part of this is to say, all right, here I've got x times 4x minus 9, and then I'm adding 2 times 4x minus 9. Well, that means I kind of have two things here and they both contain the same factor. They both contain a factor of 4x minus 9. So let me pull that out as a common factor. If I pull a 4x minus 9 out of the blue stuff here, I'm just left with x. And if I pull a 4x minus 9, if I divide this by 4x minus 9, I'm just left with a plus 2. So it looks like our two factors are 4x minus 9 and x plus 2. And there we go, we factored it. So our denominator, 4x squared minus x minus 18, really just equals 4x minus 9 times x plus 2. And there we go, we've now factored the numerator and the denominator. So really all that's left to do is write this out in its factored form and see if we can find the factor that tells us the vertical asymptote. Because don't forget, that's what we're trying to find, the vertical asymptote. So here we go. This means now that y equals, my numerator we figured out could factor to x minus 5 times x plus 2. Our denominator we just figured out factors to 4x minus 9, x plus 2. Okay, so we're looking for a vertical asymptote, a value of x that the graph approaches but never reaches, okay? I do see two things in the denominator that would give us non-permissible values. But are both of these going to be vertical asymptotes? No, you're right. This factor is not associated with a vertical asymptote because if we were to simplify this, it does simplify out, right? And so it is still an NPV at x equals -2, but it's just a point of discontinuity. It doesn't influence the overall shape of the graph. It just gives us a hole at x equals -2. However, this one here, 4x minus 9, that's not going to simplify out of this equation. That is a part of this equation, right? Even after simplifying. So that's going to be where we get our vertical asymptote. It's a factor that appears in the denominator only, right? So we can see here like this, we have a POD when x equals -2, not a vertical asymptote. Point of discontinuity, not a vertical asymptote, because that factor appears in the numerator and the denominator, so it would cancel out. But this one, this factor, VA comes from this factor. It appears in only the denominator. So what does it tell us? It tells us that 4x minus 9 cannot equal 0, right? And therefore 4x cannot equal 9. Divide both sides by 4, we get that x cannot equal 9 over 4. We're going to have a vertical asymptote at x equals 9 over 4. X can approach 9 over 4, but it can never actually reach it. Okay, now it said to the nearest hundredth, we found it as a fraction, but that's easy. We just, 9 divided by 4 is 2.25. So to the nearest hundredth, the value of k, where k just represents this in the equation for the x-intercept, or not x-intercept, vertical asymptote, is 2.25. And there we go. So if this were the diploma and we were filling in a Scantron, or if it was Smarter Marks, we would just type in 2.25. And then if it was the diploma, we had to fill in our bubble sheet. We would fill in the 2. This little one here is the decimal, remember? So decimal 2, 5. There we go. Right? So all we had to do was factor it and then look for the factor that appeared in the denominator only and didn't simplify out, because that will tell us the vertical asymptote. All right, folks, and the last thing to talk about here, we're just going to circle back to the horizontal asymptote. Really, it's nothing new here. It's actually the same thought process, but I just want to circle back because sometimes you're asked to find the horizontal asymptote, and it's not in this form. Okay, now it really is still thinking about the same things, but I know when it's in this form, it's really quick to just say, okay, it's going to be at K, and then sometimes you get hit with something like this, and you're like, oh, there's no K. How do I know what the vertical asymptote's going to be at? But if we remember the definition of a horizontal asymptote, which is just a value of y that the graph approaches but does not reach as x approaches plus or minus infinity, then we can pretty quickly see how to find the horizontal asymptote. We really are, all we're going to do to determine the horizontal asymptote is really just imagine what will happen to the equation as the absolute value of x gets very large. In other words, as x goes to positive and or negative infinity, right? That's really what we can do here as well, right? As x goes to infinity, this part basically becomes 0. So y is, well, shouldn't say it basically becomes 0, but it approaches 0. So y is approaching 0 plus k, or k, right? And that's why the horizontal asymptote is at y equals k for those ones. But when they don't look like that, we still apply the same thinking. So for a rational function, there's basically three things that could happen as x goes to plus or minus infinity. The numerator might get larger. I'm going to say quote unquote faster. Like the numerator gets bigger at a factor greater than the denominator. So that's going to mean, think about it. If our numerator gets bigger compared to our denominator, both are getting bigger because x is going to infinity, but the numerator is getting bigger like faster by a greater factor. When we change x by a given amount, the numerator has grown more than the denominator and it continues to do that. Then the equation, if our numerator is getting bigger, y is getting bigger, right? Y equals that fraction. So if the fraction gets larger with a larger numerator, then y is just getting larger. It's also going to blow up to infinity or negative infinity. But it's also possible that the opposite happens. The numerator actually gets larger, slower relative to the denominator. Well, in that case, the denominator is kind of outgrowing the numerator. The numerator can't keep up. And so as x goes to infinity, the denominator is just getting larger and larger and larger relative to the numerator, meaning that our fraction is getting smaller and smaller and smaller and closer and closer and closer to 0. So that could happen. The numerator and the denominator might get larger by the same factor relative to each other. So as x gets larger and larger, the numerator gets larger and larger, the denominator gets larger and larger, and they do it kind of at a similar rate. And so in that case, the equation is going to approach a constant. One isn't really pulling ahead of the other. Okay? But you might be saying, so how would that happen though? How would the numerator get larger, faster, or slower if x is approaching plus or minus infinity for both the numerator and denominator, right? Like both of these are going to infinity as x does, so how could one be faster or slower? And if they're the same, what does that mean? Okay, how can we tell? Well, we've kind of thought about this before when we talked about like the effect of the leading coefficient and the degree on a polynomial function. It's actually a similar thing. It's all going to come down to the degree of the numerator and the denominator. Let's kind of investigate this. 3 examples. So I'm going to show you right off the bat. In this first example, the degree of the numerator is 2. The degree of the denominator is only 1. So the numerator has a greater degree than the denominator. In this one, vice versa. Denominator has a degree of 2. Numerator only has a degree of 1. So the denominator has a greater degree. Here, they both have the same degree. The numerator and the denominator have the same degree, 2. So let's think about what that means one at a time. Okay? Here, as x goes to infinity, that x is getting squared in our numerator, but it's not in our denominator. As x approaches plus or minus infinity, the values of x are getting squared in the numerator. Well, that's going to make the numerator larger for a given value of x, right? At smaller values of x, this -1 or this +1 might make a difference. But like, think about when we start getting to like 1,000 or 1 billion, right? 1 billion squared minus 1 is still a huge number compared to just 1 billion plus 1, right? 1 billion squared is 1 billion times larger than 1 billion, right? It's 1 billion times 1 billion compared to just 1 billion. So for example, just to look at some numbers, actually putting them in, like when x is 1,000, the numerator is 1,000 squared minus 1, which is 999,999, because 1,000 squared is 1 million, okay? While the denominator, well, it's also getting bigger. It's also x is 1,000. It's just 1,001, which is much, much, much smaller than 999,999. So our numerator is getting bigger by a much larger factor when we let x go to infinity, right? It's because x is squared in the numerator. So there's an extra multiplication by a factor of 1,000 in this specific case. That makes it about 1,000 times larger. And because the largest exponent on x is greater in the numerator than in the denominator, the numerator is always going to be larger for large values of absolute value x. And more importantly, the larger x gets, the larger the factor by which the numerator is greater than the denominator, right? For example, when x is 1 million now instead of 1,000, instead of our numerator only being about 1,000 times bigger than our denominator because of the fact that x being squared, it's going to be about 1 million times larger than the denominator, right? This is 1 million times 1 million, This is just 1,000,000. Well, that means it's about 1,000,000 times bigger. Keep extending that. What about when x is 1,000,000,000? The numerator is about 1,000,000,000 times larger than our denominator. So if the numerator is just getting larger and larger and larger compared to the denominator, then overall this fraction is getting larger and larger, and therefore y is just getting larger and larger, and it's approaching infinity itself. So that means as x approaches infinity, so does y. Y doesn't just approach some value. There is no horizontal asymptote, because y is not just approaching some number. It's going to infinity, right? It's always going higher or lower. Okay, now take a similar logic and reverse it here for this one, where the denominator now has the greater degree. So as x approaches plus or minus infinity, the values of x are getting squared in the denominator, making them larger for a given large value of x, right? Same logic here, except now we're thinking about the fact that the denominator is being squared and the numerator's not, right? Even use the same numbers. When x is 1,000, the denominator is 1,000 squared minus 1, which is almost 1,000,000, while the numerator is 1,000 plus 1, which is 1,001. That's about 1,000 times bigger on the denominator than it is on the numerator. Makes sense because there's an extra multiplication by 1,000 here. 1,000 is getting squared here. It's 1,000 times 1,000. So because x is squared in the denominator, an extra multiplication by a factor of 1,000, making it roughly 1,000 times larger. And same logic, because the largest exponent on x is greater in the denominator than in the numerator, the denominator is always going to be larger for large values of x. More importantly, the larger x gets, the larger the factor by which the denominator is greater than the numerator, right? Same as we talked about before, except now it's the denominator that's much larger than the numerator. When x is 1,000,000, our denominator is now roughly 1,000,000 times larger than the numerator, because it's 1,000,000 times 1,000,000 versus just 1,000,000. When x is 1,000,000,000, the denominator is about 1,000,000,000 times larger than the numerator, right? So as x approaches plus or minus infinity, y is now going to get smaller and smaller and smaller, approaching 0, because we're dividing by a number that's getting way, way larger than our numerator, right? If your denominator is much bigger than your numerator, you're getting a really small fraction, and y is just equal to that fraction. So when this is like 1,000,000,000 squared, and this is only 1,000,000,000, we're getting closer and closer to y equaling 0. We'll never get there because the numerator won't actually be 0, but we're going to get closer and closer and closer. And so what is y approaching as x goes to positive or negative infinity? In other words, what is the horizontal asymptote? It's going to be approaching 0. The horizontal asymptote will be at y equals 0. Okay, now the final case here, what if they actually have the same degree, right? Well, neither the numerator nor the denominator really grows any faster than the other, right? Increasing x by some given amount will increase the numerator and denominator by essentially the same factor. If I make x 1,000 here, it's getting squared. If I make x 1,000 here, it's also getting squared, okay? However, in this specific case, we can see that that 1,000 is always going to get, or that x, I should say, that x squared is always going to get multiplied by 2 in the numerator, and it doesn't get multiplied by 2 in the denominator, right? For this example, we can see that the numerator will always be roughly twice as large as the denominator, because x squared is being multiplied by 2 in the numerator, but not in the denominator. Just putting in some numbers to think about this. When x is 1,000, the numerator becomes 2 times 1,000 squared plus 3. 2 times 1,000 squared is 2,000,000, plus 3 is 2,000,003. While the denominator doesn't have that multiplication by 2, its coefficient on its largest term, its leading coefficient, is 1. So it's just 1,000 squared, which is 1,000,000 plus 1. It's not 1,000,000 times 2, right? So that's about 1,000,001. And you can see numerator is roughly 2 times bigger than the denominator. Now, not exactly 2 times bigger, but roughly, because we're always multiplying that largest exponent term with x by a 2 in the numerator. And we're not doing that in the denominator. And so the larger the absolute value of x gets, the less of a difference the plus 3 in the numerator and the plus 1 in the denominator make to the ratio, right? Like for very large values of x, the 2x squared and the x squared are by far the largest contributors to the overall ratio. So if we think about it, right? Like when x is a 1,000, like we saw, and really 1,000 is not even that big. We could think about a billion or a trillion or a quadrillion, right? We're going up to infinity. So like 2 million and 2,000,003 really aren't that far off in the grand scheme of things, right? 2 million divided by 1 million versus 2,000,003 divided by 1,000,001. The +3 and the +1 don't make as much of a difference. So what are we really approaching? Like what's dominating the behavior of this function or the size of this numerator as x gets very large? It's the 2x squared, right? That's by far the biggest contributor to the size of the numerator. And the x squared is going to be by far the biggest contributor to the size of the denominator at large values of x. When x is much smaller, the 3 and the 1 do make a noticeable difference, okay? But it's just going to approach, and again, it won't reach it because of the +3 and because of the +1, but it's going to approach the ratio of 2x squared to x squared, which is 2, right? 2x squared over x squared is 1. So the equation is just going to approach a y value of 2 as x gets larger and larger. Meaning that as x approaches plus or minus infinity, when we have an equal degree in the numerator to the denominator, y is actually just going to approach the ratio of the leading coefficients. And there's going to be a horizontal asymptote at this ratio. So again, it's just about, all right, same degree. So they're both kind of getting bigger by the same factor, except for the fact that this gets multiplied by 2 while this gets multiplied by 1. So the ratio of those is 2, right? If this were a 3, it would approach 2 over 3 because this will be bigger by a factor of 3 compared to this thing's factor of 2, right? When this is like 3 million roughly, this will be 2 million roughly. And the ratio of 2 million to 3 million is going to be 2 over 3. It's approaching that. It won't get there because it's not actually going to be 2 million. It'll be 2 million plus 3, right? And this one, if there was a 3 there like this, it'd be 3,000,001. So it's approaching a ratio of 2 over 3, but it will always be slightly off. And that's why we have a horizontal asymptote there. So just a little summary here, okay? Could have just given you this, but I find it gets into the territory of just memorizing, which I don't like, okay? It's good to understand where it comes from. But here's kind of the things we look for when finding the horizontal asymptote. It comes down to the degree, because there's 3 things that could happen. So if the degree is the same in the numerator and denominator, the horizontal asymptote will be at y equals the ratio of the leading coefficients. Okay, because the leading coefficients are attached to the highest power of x, and those highest powers of x dominate the equation's behavior, or rather, they dominate the size of the numerator and the size of the denominator. If the degree of the numerator is greater than the denominator, well, then our numerator gets like bigger faster than our denominator. And so it's just going to blow up to infinity, right? The denominator can't keep up with the numerator. The numerator keeps getting bigger and bigger relative to the denominator. And so it shoots off to infinity. There will be no horizontal asymptote. As x approaches plus or minus infinity, so does y, because the numerator is just getting larger and larger compared to the denominator. But the third case, if the degree of the denominator is greater than the denominator, then it's reversed. The numerator now can't keep up with the denominator. The denominator is getting larger and larger, faster and faster, and therefore we're dividing by a bigger and bigger number. Our fraction is just getting closer and closer to 0. So our horizontal asymptote will be at y equals 0 if the degree of the denominator is greater than the numerator, since the denominator gets larger and larger compared to the numerator as x approaches plus or minus infinity. And honestly, folks, when in doubt, you don't have to like try to think about it too hard or try to remember these. I don't even want to call them rules because they're not rules. They come from thinking about it. But like when in doubt, put in 1,000 for x, or put in 1 billion or 1 million for x, and see what the y is approaching, right? If you try putting in 1,000, you'll see that this just keeps getting bigger and bigger. When you do 1,000, if you do 1 million for x, you'll see that the value of y just keeps getting larger and larger as the output, right? Here, when you put in 1,000 for x, you'll find that it's pretty small. It's going to be like very close to 0. If you try putting in 1 million for x, you'll see that it gets even closer to 0, right? And here, if you put in 1,000 for x, you'll see the ratio is very close to 2. If you put in 1,000,000 for x, you'll see it gets even closer to being 2. So when in doubt, try just actually putting in very big values of x and see what y approaches when you do that. Okay, let's try this out. All right, so let's just try this out here with these three, see if we can determine the horizontal asymptote, if it exists, for the following rational functions. We've got y equals x plus 3 over 3x squared minus 2x plus 4. So that just means, okay, we need to think about, remember the important thing to think about here is degree of numerator versus degree of denominator. Well, degree of numerator is 1, right? Well, degree of 1, degree of 2. So our denominator has a greater degree than our numerator. So what's going to grow faster? Our denominator, right? The numerator is not going to be able to keep up with this. When x is 1,000, just from the squared alone, the denominator is 1,000 times bigger, right? When it's 1,000,000, this is 1,000,000 times bigger than our numerator. So the denominator is growing faster and faster. The numerator can't keep up. We're dividing by a bigger and bigger number. Our horizontal asymptote is going to be at y equals 0. Again, just because the degree of the denominator is greater than the degree of the numerator. Okay, there we go. Again, what did I do there? I just imagined x getting really, really large. What would happen? Okay, all right, let's try b. Ooh, okay, degree of our numerator is 3. Degree of our denominator is also 3. Okay, so one is not growing faster than the other, right? Like when x is 1,000, we've got 1,000 cubed in our numerator and 1,000 cubed in our denominator. But our numerator, it gets multiplied by 2. Our denominator, it's getting multiplied by 3, right? So like we're going to have 2 times 1,000 cubed and 3 times 1,000 cubed, right? Well, that's going to be, this will be bigger by a factor of 3, where this is bigger by a factor of 2. So our degree numerator equals our degree denominator, meaning that it's just going to come down to the ratio of the leading coefficients. So our HA will be at y equals the ratio of the leading coefficients. Well, that's just 2 over 3 then, or 2/3, right? And again, folks, when in doubt, put in really big values of x and see what y approaches. Here you'll see that it approaches 0.6667. The bigger you make x, the closer it gets to being 0.667. Because yes, that negative 4x and that negative 6x squared plus 8, they do matter. It's not like it's going to be perfectly equal to 2 over 3, but because these are so much larger than those, when x gets much bigger, it gets closer and closer and closer to just being the ratio of 2 over 3, because this is going to be most of the numerator and this will be most of the denominator for very large values of x. Okay, one more here. And I mean, we could FOIL this all out if we wanted, but what's the degree of my numerator? It's 3, right? I've got 3 multiplications of x. I would end up with an x cubed in my numerator. In the denominator, degree is 2. I just have 2 multiplications of x. So the degree of my numerator is greater than the degree of my denominator, meaning that the numerator grows, quote unquote, faster than the denominator. Denominator can't keep up with the numerator. Numerator gets larger and larger, meaning that this ratio, right, numerator over denominator, is just becoming a bigger and bigger and bigger number. So as x goes off to infinity, so does y. Meaning that there's not some value it approaches, right? Not some asymptote. There's no asymptote. So no horizontal asymptote. And there we go. So that wraps up lesson 5 and therefore unit 2. So you can now do the topic 2 quiz for lesson 5, and you can also do the unit 2 test. Make sure you book a time to do that. And yeah, as always, don't be shy. Reach out with questions, concerns, book a meeting, send me an email, whatever your preferred method is. But there we go.